that they have to take. They just traverse the network, and it's up to each node to figure out how to send the packet along the rest of the network. So depending on how busy the channels are inside of the network, you can see here that the little red guy, he goes node A, node B, and all the decisions are made by node A. The hardware inside of here uses queues. So first in, first out, the packets arrive in, the nodes figure out where to send them next, and they keep going until they arrive. Part of this concept was when the message gets to the host, there's no guarantee in what order the message is going to arrive. It needs to be able to be stitched back together in the way it was sent. So you can see that right there. So that's concept one, packet switching. Concept two, they did not have a cool GIF for, which is very sad, but it's called best effort networking. And best effort networking basically means I'm going to send the message and I'm going to forget about it. I'm not going to worry about whether or not it's arrived. I'm not even going to worry about if it's corrupted when it's arrived. I'm just going to send it. So it's up to each node in the network to pass along the message and then forget about it. What's the advantage, why this is a big deal in the internet, is it maximizes the infrastructure. So if we can go back here, if you can imagine a circuit switch network where we have to establish a path, an actual circuit through the network, that's going to place a lot of processor and memory strain on the network, because when we establish a connection, we're going to have what they call a stateful connection. Do people know the difference between stateful and stateless? A stateful communication means you and I both know what's going on. A lot of you are from different cultures in the US, and so you guys actually practice stateful communication. There are polite ways of communicating that you guys engage in before we can get down to business. I'm from North America. We engage in stateless communication. We're just gonna do things however we want, and that's gonna be that. For example, I've had some experience in Latin America. When I would go to church in Guatemala, I would shake everyone's hand in church. And if I didn't do that, I was considered very rude. When I go to church in Gibbsville, Wisconsin, I don't have to shake everyone's hand and no one thinks I'm rude. So anyways, statefulness, when you have a stateful connection, sorry, this is kind of roundabout. When you have a stateful connection, you have to negotiate the connection, the route that it's going to be, and that takes a lot of resources on the network. So packet switching, or excuse me, best effort networking just says we don't even care. Just try to get it there. The interesting thing about best effort networking and the way or why it allows the internet to work is we're actually allowed to make up for it later on. And we're going to get to that right now. Can someone shut the door, please? Thank you. Protocol hierarchy. So one of the 7 big ideas of computer science is abstraction. And that is we take a concept and we just talk about it at a theoretical level, and then we worry about implementing it later. In protocol hierarchy, we have different responsibilities of networking spread across layers. There's 2 big models of protocol hierarchies. There's OSI and there's TCP/IP. OSI is a very intelligent model. It was developed by researchers in Europe and the US, and TCP/IP was developed in the US. Guess which one won in the internet? TCP/IP. The Americans said, nah, we don't like that. We're not going to do that. And well, anyways, that may be changing on the world stage, but back in the 1970s, we got our way. So we have TCP/IP. There's 4 layers: the application layer, the transport layer, the network layer, and the data link layer. This message over here is from a program called Microsoft Message Analyzer, and it's showing the traveling of an HTTP message across the protocol hierarchy. You can see at the top we have TLS, which is just HTTPS. It's a secure version of HTTP. We have the TCP, which is right here. We have the network and IPv4. And then we have the data link layer, which is the network card, which is called Ethernet. So the application layer, HTTP, a user requests a website on a browser. So in this example, I gotta skip forward. Where am I going? I think I was requesting a picture from something on EC2. So that's the Elastic Cloud Storage that Amazon has. So this is a server that I manage talking to EC2. So you can see here, this is actually part of the way through what they call a server and client hello exchange. And in a server and client hello exchange, In the HTTP protocol, the client and the server are basically figuring out what sort of HTTPS protocol and cipher suite they're going to use to talk to each other securely. So you can see here we have a TCP connection open. And the important thing to notice, here at the bottom is we have a data payload that's formatted in the HTTP protocol and it's encrypted. We're already far enough along in the TLS handshake that the client and the server know how they're going to encrypt and decrypt messages with each other. They've already exchanged keys. And so what's going to happen is the application layer is going to open up a socket in the TCP layer. So we're going to go from here to here. The TCP layer makes up for best effort networking, whereas best effort networking says, I really don't care if the data is corrupt or if it arrives. They came up in the TCP IP model, they came up with a way to account for that, and it's called TCP, so Transmission Control Protocol. It has mechanisms built in to make sure that the data arrives, that it's not sent repeatedly, and that it's not corrupt. And you can actually see that right here. You can see right here in the TCP packet, there's sequence numbers and acknowledgement numbers. That's the client and the server making sure that the messages they want to exchange back and forth with each other have actually arrived. You can see right here, TCP works off of the concept of ports. Since we're doing SSL communication, we're talking over port 443. If you've ever worked with anything on the web, you know that SSL or TLS communication always happens on 443. You can see right here that the encrypted HTTP request, I'm guessing it's probably a GET request, is right here as a TCP payload. So we have two parts of the packet per the packet switching model. We have the header, which basically says, here's where I'm off to, and we have the payload, which is the encrypted message. The cool thing about this is as you traverse up and down the layers, they all get wrapped up or unpackaged by the other. So HTTP gets packaged. The whole thing from the HTTP handshake is getting packaged into the TCP layer right here. The payload from the TCP layer is packaged right, actually I couldn't find it. Sorry, I couldn't, let's see, where am I at? I couldn't find it in here, but this is the IP layer. This is the networking layer. So everyone knows what an IP address is, right? All computers on the internet, an IPv4, we identify them by IP numbers. So we have the IP number, forgot to expand it. If I'd expanded the destination address at the top, we would see the IP protocol talking about the IP number. So what it's getting ready to do is it says this needs to go here. It's going to get passed down to the network card. And you can see, do you see the MAC addresses right there? Every network interface that's connected to the internet has a MAC address that identifies it. So what it's going to say is, I need this IP to go to this MAC address. So now it's going to send it on. And so then it's going to traverse down here, and then it's going to go on to the next data link layer, which is probably going to be in Concordia's network. There's going to be a gateway that it hits. Does everyone know what gateways are? Gateways basically allow different IP subnets to talk to each other. So it's going to traverse through different gateways inside of Concordia's network until it hits the backbone. Does everyone know what the backbone is? The backbone is the internet. So, sorry, I was learning about all this stuff as well. The packet's going to traverse its way through the routers of the backbone. The routers of the backbone in the internet, who do we use here? We don't use a big internet provider. I can't remember the name. They're very specialized hardware that have something called routing tables in it. So you give, a packet arrives inside of a router, it looks at the header and says this is the IP, and it figures out this is the next router or network I need to send this thing to in order to arrive. Eventually, the data is going to find its way to the host, and it's going to traverse its way back up the layers. And each layer is going to unpack what was in the layer below it. So the data link layer, that's frames. That's like literally binary frames. That's going to be translated into the IP layer back into packets. The TCP layer is going to present that to a socket in the browser or on the web server that's listening for HTTP requests. And it's going to unpack it at the web server. And the web server is going to take that with its server certificates, decrypt it, and figure out what to do with either the HTTP GET or POST request. So let's see. I was going to do a small demo here.
We're already at 12 minutes.
Am I at 12 minutes?
Yeah.
Okay. Well, we'll stop this. Just so you know, there's Yeah, there's a lot of negotiation that goes on into a HTTP SSL request. I'm going to pick on the computer science department. If ever you work in university IT, one thing you'll find out is the IT department and the computer science department pick on each other. So this is the computer science website here at Concordia. So we're going to run it through here. This is the SSL Labs tester. If you're ever running this on a website you don't like, or that you do like, and I do like your website, by the way, make sure you click the little thing that says do not show result on the board. So we're going to do, yours is going to go slow because of that one. We'll do the Concordia website. What this website does is it tests the SSL strength. It's basically testing how well the admins have secured their website. I use this to make sure that I'm not like leaving web servers open to hackers. And if you do a bad job, it gets posted on their boards and it'll be an F. And I always feel like there's probably people watching this thing and they're just like, oh, I should go attack this thing right now. So let's see, let's go back to the start here. Yeah, you can see right here. If your site's not secured well, it's going to end up on this site. And I never want to do that to anything that belongs to Concordia. All right, I guess I'll end here. But what it's going to do is you would actually see a TLS handshake in all its glory because they're going to agree on something called PKI, which is public key infrastructure. It's basically the way that two servers, a client and a server, authenticate themselves on the internet using X509 certificates. They're going to agree on cipher suites. That's basically how are we going to encrypt the data so no one can read it as it's going through the IPv4 layer and the TCP layer. Those are the layers that basically the internet's running on. People inspecting those packets won't be able to read them because they're encrypted. And so there are good cipher suites and there are bad cipher suites. And that's really what this is analyzing. This is analyzing the web server that we use here at Concordia. And it's saying, if I talk to you, how secure is the data going to be? And it'll actually be fairly secure. And since I'm already over time, I guess I'll go ahead and end there. There's more to say about Diffie key exchange from last week because it's really important. It's something that you'd see on here called forward secrecy, but we'll leave that for another time. So questions? Call it good.
All right. Next.
While the next person comes, we'll see what Concordia gets. I think we're going to get a B. I hope we get a B. B basically means you don't implement forward secrecy real well. Yeah, we're going to get a B. That's actually a fairly good mark. That means you're safe. By the way, this all goes away. I don't know how to pronounce it. Is it the Shor algorithm in quantum computing?
Oh, Shor's algorithm.
Yeah, when Shor's algorithm comes along, everyone's getting an F. So anyways, maybe someone else will talk about that. All right.
I loved him very much.
Okay. So technically, this title doesn't match what I'm talking about. Well, it's just because when I was thinking about the question is yes, let me start. So when I was thinking about network, I was trying to say, okay, what could be the future? So say we are right now, none of us, I think, is really using 5G network, even though you have the phone, but you don't really have a provider for the service right now. At least there's no really large scale for 5G. But why we have 5G? I think last year I have talked with Dr. Littman about it. They say, just say, it seems like so bright about the future of 5G, but why we need 5G? So do we have to jump from 4G to 5G? Then that's the question. What's the future of it? But when I was searching that, people told me, okay, people are still thinking about 6G now. So what's actually G means? Wait a second. Oh, okay. So you definitely heard of 3G, 4G, 5G. So G is in general just a generation. So it's a short name. So 3G is after 2G, 4G is after 3G, 5G is after 4G. But everything is people making agreement. Okay, now the next time, the cellular wireless network connection, we're using all the standards. So it's a package of standards. So what's the difference between the different generations? Some about the systems, but the more customer, we are talking about the speed and what technology they are using and what the frequency of the wave they are using and what's the latency in behind. And all you can see about this. If you heard of that, they are definitely making some stations for the waves. So then that question is, we have a 2G, 3G, 4G. Does everyone heard of 1G? Perhaps no, because they don't need to claim that they are 1G. But it was during the 1970s, the late 1970s. The Japan is the first one to making the commercial network of so-called 1G, for the first generation of wireless network. So there's a small, not really small, there's this big table about something about that. So there are a lot of things technically wisely, but there's something noticeable. I put a red circle, is about speed. Definitely you can see the speed is increasing. Also, if you go down to the kind of the last row, you will see in 1G, technically that's using, there's only analog data or signal is transmit between the network. So there's only voice. The second generation have the short message and there are signal, there are data then. And 3G, they add more capabilities, and 4G is still on top of 3G and 5G. You can see they are all talking about the feature, but none of it really talking about why it making it different. So there's another table of that, definitely still a very simple one, but there's something I just want, I'm interested in is they are talking about the frequency. So in 1G and 2G, you can see it's in 800 megahertz, and now then later it's evolving to 2000 megahertz, and 4G, if you are using the raw Wi-Fi router, you already heard of 2.5 gigahertz, kind of this spectrum. And also nowadays you will see 5 gigahertz spectrum in your raw Wi-Fi, and people claim it's better than 4.5 G. And then the 5G in US will be 28 gigahertz, much higher than before. And 6G is even higher. And the frequency of the electronic magnetic wave is matching the speed increasing. Not really say linear matching, but you can say when it's one increase and another one is also increase. So technically that's because the more frequent, the highest frequency it is, the more data it can be passing. So you can create more length and sample during inside the wave, so it means can transport more data. Also, the last line is talking about latency. That's another thing. That is something why we want high and high frequency. When we are speaking about 4G to 5G, what's the biggest thing change is not only the speed increase, but also the latency reaching a stage that will making almost like a real-time communication more make sense. So here is a short picture about what the different waves and what is the application of that. So from the left side is the one with the highest wavelength and the least frequency. And on the right-hand side, it is a less shorter length and a higher frequency. Something in the middle, we can see that is a visible light. And on the left side of the visible light, that is a so-called terahertz waveband frequency. So that is what we are talking about when we're reaching the 5G. Now we are starting using terahertz bandwidth. One thing interesting here is actually we are actually getting closer and closer to the light we are talking about. So definitely there's a limit. Until a point, definitely we won't increase anymore, or we are using a different way to transfer data rather than the cellular network. So let me talking about another thing is why we want more frequency. I already talked about the high frequency, it have a higher data rate and also has a higher capacities. It means more length at the same time, and also lower latency. But the low latency is kind of because of the data rate and also because of the less data queuing delay. So it makes it quicker. And also on top of that, during the 1G and 2G, at that time, there is no internet, or at least it's not built upon internet. But 2G, but starting when we're having data, actually, just like we are talking about the HTTP, we have a package switching. Technically, the cellular data has to go through switching to internet, then going back to the other user. So technically, there are more steps in between. But the newer technology also make it less kind of process, less gateway to travel, and also making it a lower latency. And another thing is, the last one is I think people, if we go back to physics, we will see. So you can using a paper to block your eye, and you can see nothing. But like the sound, you cannot blocking with just not that easily. You can blocking the sound. It's just like the longer the wavelength it is, the kind of the wave can go through the obstacles easier. So the higher frequency also means it is going more straight rather than going across the obstacles. And also the energy will going down quicker. That is a shorter effect, but it has some good things too. So let's talk about something about application. So we have wireless fiber. It means because the high frequency, you can directly connecting one another and with higher speed. Another one is if you go down to the left corner side, it's called intra-device radio communication. So you can think about if your whole computer inside is not connected by the bus, but by say terahertz wave communication. And the information shower, it just means because the speed of the network become increased. So actually it's outputting more data. And also it will be used in connectivity in data center the same as I talk about the just inside, say if it's inside device, but if it's in a home, in a room, like a data center, then we don't need to using the cable to connect. Here is also a small graphic about the distances between the frequency and how the frequency affecting the power will be getting lost by traveling the distances. So the higher frequency it is, the easier, the higher part, kind of it's dropping the energy quicker, losing the power quicker. And also it's talking about the penetration. So in short, the high frequency is a two-edged sword. They have some good, there are some advantages, but it also have some shortcomings. Another reason why nowadays we having this terahertz wave is because the device that to generating terahertz wave is also getting cheaper and cheaper. So now it will be much easier to affordable than before. But we will still hear the news saying the 5G cell phone actually consume more power much quicker than if it's under the 4G network. It's also related to that. You need to have more power to generating the high frequency of the wave. But also speaking of that, there is an advantage that of the high frequency wave is because actually it can travel less distance, or at least it doesn't affecting longer distance. It means, in fact, it will be getting less chance to be interfered by other data source. Say, like the terahertz wave, actually the cover distance is only 100 meters, or you can, I don't know how to convert it into feet, but anyway, it's a kind of very small area. So it means, but I think it is like a 40 feet, 400 feet. So in not too far, too long away. So it means it's covering only a kind of your eye can see the distance. So it means even though there are the same amount of the people using the 5G network in the area, actually it will be getting less chance to be interfered by people just a little farther away. But instead, if you're using 4G, technically that is, I think it's a double the distance, like several kilometers, or can say several miles in range. So that means it'll having more interference between each other, more noises. So then the next thing is about what is a possibility. So why we are going to using 6G? It's really talking about when we are thinking about nowadays internet of for service, internet of for infrastructure, internet of for technology, and eventually internet of everything. So your cars on the net, here is also something talking about, so what if in future we have brain-computer interactions? So it means the latency will be really sensitive. You won't really say, I'm thinking about this, but why it's taking a second to react? It will making the user experience pretty bad. Also, nowadays we having a lot of VR devices. Sometimes some of the thing is, what if we can get rid of all the cables? What if the data can transfer quicker? What if the latency can be shorter? And what if we can not only see and hear, but also smell and touch? The more data it is required and the more sensitive the user requirement required, it means the latency and the speed still become a key to make it to pushing the market. Not needless to talk about the telemedicine. So I'm also thinking about that. If someone is doing a heart surgery, and what if the doctor take a little longer to see, oh, I cut it too much? That will be really bad. So that also means a lot of we having endless requirements on latency and on the speed for the application. So here talking about sounds and
I'll
also
let you know you're over 15 minutes now.
15.
15.
Okay. Okay. So it's almost done. So everything is about. So anyway, 6G still have some usage, and there are some other things will driven its work, but you can see that the trend is keep on going. And also we believe 6G can having better user experience compared to 5G. And here is also something like almost a lot of places in the world has already said research on that. So that's it for my presentation. So I was just trying to figure out why we need it. So apparently there are some uses. This one or the next one?
So the 6G column on each of them, are these just predictions, or is this like kind of what Dr. Walker talked about with theory, and it's not, you don't have to technology for it yet?
So
Or like, where is it
actually
coming from?
the backend technology is there, but people just don't know how to put it up and how to make it be say affordable or like everything will be connected. So of course there are some more or less research is there, the theory has there, but they are still making technology.
So the 6G towers, is the theory behind it that the towers link to each other? I know right now,
Yeah.
cell towers are all.
The fact is, as I mentioned before, based on the frequency increase, the wavelength is getting shorter and shorter. So you have to build more and more stations.
Right.
So now it's so-called a small cell station. So almost like every 100 feet, there will be like small things you probably know, just hanging up on maybe on the traffic lights or somewhere, because they cannot travel too far. Otherwise, it's just gone. What's up?
So I like how the fact I talked about circuit packets issue and then talked about that film.
Yeah.
But no, I read which countries will go first. I read that the United States military won't let 6G happen there because they use the frequency.
Yeah, exactly. That's a point. So you can feel it's actually a competition still. Like, if you really speaking of that, I would rather say China will leading because China have no such concern. They don't read about the legacy thing.
So the PLA is not going to say no.
Well, they will just, I would say, which make it more sense for as a whole country rather than making money, then it was doing that. And actually, that's the difference is, so China like actually, it's mentioned like trying to using government pushing that. So I bet that's a different story.
Yeah. So the Army's got to be.
Yeah. Okay, any other questions? Okay, then. Give me a second. How do I start closing? Stop sharing.
Don't all go at once.
I can go. Oh, that's funny. That's
Can you hear me now?
Yeah, I can hear you.
All right, so then network infrastructure has all these components and everything's connected, right? If you have a server, it will probably mostly have a WebSphere or an instance that's going to support a database, and that's going to be supporting a application as well. So to manage all this, when it comes to what is connected to what, the answer is much harder than just say another hardware, right? Because we need to have a notion of impact. And for that, we 1990, when ITIL first came out, ITIL is a framework for service delivery and IT management. When it first came out, they also invented the CMDB, which is a configuration management database. A configuration management database has information for configuration items, including the IP address, the name, the classes, and everything that this configuration item has, and that's living in your network. So if you have a server, a configuration management database is going to have all the information of a server. If it has a database running in that server, it's going to have all the information of that instance that supports the database as well. And that's basically what a CMDB does. However, by itself, a CMDB is just a database. It does not, it's nothing really new, right? And however, it is able to map your entire relationship that has between whatever configuration item you have out there. And right here, I wish I had this picture 4 months ago, but right here, it's a perfect example of how a configuration management database reproduces the relationships of configuration items inside a network today. So everything obviously starts from the network here, and it goes through the servers, to the middlewares, and sometimes straight to the database, and then to the applications. It's very simple, but when you go to a company and you send a discovery in a network, you gotta find the minimum of 300,000 configuration items out there. And if you think how many things we have in our own network at home, it's really crazy how much is hard to manage all these and understand how complex and all the possibilities of impacts that it has. Because for what, so just anticipate a little bit why it needs to be done. Because if this server goes down, for example, we need to know what is the impact for that in our company, right? So if application is going to go down, how much that's going to cost per hour in a company, and how many hours that need to be back on. So all this is important. But however, the only biggest problem is that the implementation for that is most likely to fail 85% of the time, because a configuration management database requires that other sectors of the company follow processes. And as we know, we are really bad following processes because we are in IT or we are developers and we don't like to follow processes. So, and 85% of the code that we have out there today is failing for configuration management because of this first step. And the second step is the time use case. It's okay, but like today, my manager was saying that by next year, he's going to become IT master, and that is only 100 IT masters in the entire world. So that there is a huge lack of people that know how to define use cases and actually have the knowledge of how to deliver IT services by the company, which is basically run by our entire operations in our organization. And we define CI times that it already exists for 10 years or more because most of the configuration items are on-prem, not in cloud, and make sure that you can discover it. It's a big thing that I'm going to talk soon. And the file administration process and ownership. for the entire configuration in your network. But by itself, a CMDB is just a database. However, in the past 10 years, they decided, and this company here that I'm presenting now, they created, they have a patent for a discovery module that they throw in your network and discover everything for you every day. So then, if a server is down, no one needs to call and tell my server is down, we need to do something about it. The network itself is going to treat something and create anything, for example, in your company. And it is very simple. All it needs is a server that's not actually a server, this is JavaScript software running a server. And the instance itself, and that has a program records that sends and receives messages, and sensor that is just sent by the root server to the instance, and that's going to be doing every day. So all you need is the IP address, all the IP address that you have to go and figure out there, and credentials to go inside this IP address. And these modules are able to just see anything alive in your company, from a laptop to a server to a database, everything. It's not able to see your application itself if you don't program for that, which is the hard thing. It's the only thing that's being done manually on today's world, but the rest is all done automatically, so it's pretty good. And why to manage a network? So first thing is calculate impacts, like I said before. If application about some companies, especially healthcare or top companies, they can have the applications out for nothing. Guys, they lose an absolute amount of money. And when you have a view like this, you are able to see, and even if you're a developer, right? You're going to make a change in a software, you have to go to change management, right? Yeah, so change, when you go to change management, you have access to something like this, you see what's going to be the changes that are going to be impacted by whatever you're going to update. So this also helps with that. You have control of relationships. You want to migrate from one side to the other, and we're able to manage the CIs better and evaluate changes. And you also are able to have another module. I don't want to get into it, but you're able to have a better view of attacking the work that would be related to incidents. So my conclusion for that is that IQ is being not only IQ, but implementation of CMDB, also because of processes. But unfortunately for me, companies need people that works with them, because at the same time, that's very hard to implement and very expensive. It helps save a lot of money for the company, because you're able to predict things or solve things in a shorter term. And I took the time to share this link with whoever have ever had any interest in access these type of services. These companies, ServiceNow, they give free developer instances for people to go there, and they usually have everything developed in JavaScript. So if you know JavaScript, you are able to go and work on something like that. They offer free courses, and they don't have many people that know how to do the job. And I guarantee that most companies that you guys are working or know today are probably using this company, because they are one of the only ones on the market. That's it. Any questions? No? I know how to answer today.
Next up, then Maddie. Get a random number generator. It is random. It was number 10 then number 3 on my list.
Okay, got it. 11 minutes.
No, you're fine. Had to fix your audio.
But that's my fault. I need to get out of here.
Good? All right. So I'm going to be talking about software-defined networking. Specifically, I want to look at the Ubiquiti Networks Unify system. But when it comes to setting up local area networks, we kind of just had a little bit of a discussion about that, but really they fell into two categories in the past. You could either go with option A, where you buy a consumer wireless router with everything kind of all included into one package, or you could go with option B, which was an extremely expensive enterprise solution that requires a team of people and software to organize and maintain and keep up with. But about the year 2014, the networking landscape was really changed. There was a new contender that came to the market, and it eventually has become known as software-defined networking. And what it does is it uses API environments to create a place where networks can be configured and reconfigured on the fly. So instead of in the past having to log into each individual device or pushing out configurations from a central server, now you have one place, one location that everything connects to, and you can do your configurations that way. Many large enterprise environments are moving towards this idea because they can reduce the headache, the management, the databases, everything that goes along with it. And it's caused a breakthrough really though for anyone who's designing a local area network, because now we can have enterprise features in places that were cost prohibitive to have those things, such as the home or in small businesses. And one of the companies that's really been leading the way on this software-defined networking concept is Ubiquiti Networks. They have a unified system. That's the name of their the system that they're promoting. And the cool thing is, it was released in early 2013, but Unify has really been disrupting the wireless market because it gives people the easy setup that one would expect with a home router, but you also have integrated into the system advanced tools that previously were only held by enterprise deployments. Companies like Cisco, HP, RS, and others have been diving into this software-defined network landscape. At Lutheran High, for example, I use Cisco's Meraki system, which is a similar product, only it comes with the Cisco price tag. So there's a trade-off with all of these products as they go into the market. Unify, however, is really the least expensive and the most fully featured of the systems that are currently on the market. And it brings what you would expect in some enterprise development. So it brings VLANs and firewalls, directory integrations with Radius, Active Directory, Open Directory, really any directory you can think of. It brings enterprise WAP2 authentication for Wi-Fi with security certificates. It brings guest portals, bandwidth controls. You can set up users and groups if you want to. You can add multiple access points that have zero delay handoffs between access points as you move around. In addition to that, Unify also has voice over IP systems and security cameras. All of this integrates underneath one umbrella and can be managed from one portal. And they all come together in really one inexpensive package where you can pick and choose the things that you need, right? Do you need 4 access points for your house because you have multi-layers instead of trying to play around with range extenders or how you're going to set things up, right? Unify puts all of this together for you. The way that it works is really cool. And Unify has a nice little video, quick little 18 seconds to show you what happens. So you take a gateway, plug it into a switch, plug in everything else, and it makes things happy. Then there's a central management console. You can see green means go, right? And things all work their way together. Now, the fun doesn't stop there though, right? Because the cool thing is I found out about Unify about a year ago or so when I was trying to evaluate different systems. And when my own home router died over Christmas break, I decided, why not? I'm a sysadmin. What's the worst that can happen? And so I ended up buying into the Unify system myself. As you can see, there's a web client that you can interface with, right? I mean, here's my home system. I'm establishing a remote connection to it now. So all the way here in Nacogdoches, Wisconsin, I'm interfacing with a little rinky-dink setup in Sheboygan, right? You can see from just the main landing page, there's a whole host of information that, unless you're not a computer nerd like any of us, right, most people don't really care about. But the setup for this was really easy. The initial setup, all I had to do was plug everything in, open up an app on my phone, tell it what I wanted to call my wireless network, and ta-da, there it was, right? And then, of course, because I am who I am, I had to go in and tweak and break things and reset and restart and whatever, right? But I mean, you notice it's been scanning all day, right? It knows the throughput loads that my ISP is allowing, the latency factors that have been going on. It's giving me an overview of what I have. So right now I have the USG 3-port router that Seth was talking about, right? The thing that does the handoff between my network and the internet. I've got a switch, I've got an access point. Right now I have 3 wireless clients connected because no one's home. I can look at my traffic distribution. So right now, all of my 2.4 devices are using channel 11. My 5 gigahertz one are using channel 36. I've been doing speed tests on a regular basis. So you can see I'm getting 15 down, 2 up. You can see power capacities because it's a PoE switch. You can see the clients that are most active. The clients that have been associated the longest. You can see the applications I use, right? I was downloading a game a couple of weeks ago, which took up a terabyte, right? Web transfers, Netflix. I do some Pinterest stuff because I guess I'm like that too. And you can see the Wi-Fi client associations. And one of the things that is integrated inside the USG is some intrusion prevention and detection systems, which was one of the things that I talked about in my previous presentation on a next-gen firewall. Now, the USG is not a next-gen firewall, but it has a lot of those features integrated into it that do make it pretty handy. Now, you notice there's nothing showing up here because my apartment isn't a threat, but if it were, you would see a graph showing where threats are coming from, where attacks are coming from, allowing you to do things, for example, like at Lutheran High, we regularly get attacked from China. So we've started to block some Chinese IP addresses because apparently Blade is trying to attack my network, right? You can go in more in depth in that, right? There's a separate pane for threat management that'll give you more details on where things come from and what they were doing. One of the other cool things with my access point is I can actually scan the network around me. So you can see all of the other access points in my apartment complex. So it can come in handy, especially if you're in a location like a business or something like that. It'll keep track of hey, there's an access point that popped up that's not supposed to be there. What do you want us to do with it? So that comes in pretty cool. You can see the clients that are associated. So right now you can see I've got this cloud key thing, and this is actually its own application server. So this is actually the thing we're connected to, this cloud key, and it's doing the running of the entire network. You can see that I have a couple of Belkin Wemo IoT light switch or light socket switches that are there. Devices. One of the other fancy things I think is you can actually get a topology map. So you can see how my network is actually built. And if I was home, you'd be able to see like an Xbox up here and a PC wired in. You'd probably see this laptop and my cell phone in the wireless side of things. And so it breaks everything down really clean, really easy, so you can see where things are. And just because that wasn't enough, there's more, right? You can actually take a look and you can import your own floor plan. And I haven't actually been able to have time to do that because, you know, I have a real job. So you can actually put in your own floor plan. You can actually place the access points where the access points are, the switches where switches are. I think they're working on even giving heat map capabilities too. So that's fun. Like I said, there's so much that you can actually see. I mean, we can go into the statistics side of things. You can see performances. You can see system statistics, who's connected where. You can see traffic statistics. So we saw this already a little bit, but you notice, you know, online gaming is a huge portion between Xbox and Steam. Network protocol stuff, so some generic HTTP requests, Google searches and things that I do. File sharing, web servicing, media streaming. And it breaks it down by things that it knows, right? Netflix, YouTube, Amazon Video, etc. Now, if that wasn't enough, I know I'm running out of time here, but there's a whole other configuration pane. And this is where I was talking about with all of those enterprise things. So you can create multiple SSIDs. You can create different groups and schedules, hotspots. You can change VPN things. You can set up VLANs. You can segment network things. The cool thing is all of this cost me $300, you know? So really for the price of maybe a high-end consumer router, you're getting all of the enterprise capabilities one could ever hope for and more. And I know Seth is probably hopping on Amazon right now.
Is it a Wi-Fi router itself? Or it just talks to your Wi-Fi router?
Correct. So the way that it's let me go back to the topography one. So the way that it's set up, so each of these pieces is separate. So there's an access point that does all the Wi-Fi handling. It's connected to a PoE switch that's then connected to the gateway, which is connected to the internet. Now, the cool thing is you don't need to have I bought these 4 pieces because that makes up really the core, but you don't have to. You have your own PoE switch, you have your own gateway, you can just buy the access point. Even if you don't have a PoE switch, the access point came with a PoE injector, and you just access the access point on the app. You can set up your network from there.
So the ideal world is buying their equipment because it plugs into their ecosystem the cleanest.
Exactly.
But if you did have your own, like you said, you had your Xbox on there, or you had your own wireless access point, an ASUS router or something like that, it would work. It just might not integrate as cleanly or something.
Your topography map will not be as pretty.
Gotcha.
And this is this thing that I've seen at work because I've been integrating a couple of Unify switches with my Cisco Meraki system, and it's totally wrecked my topography as I look at the map of things. So. Yeah, that's what I got. Questions?
Do you think this is, you said you were looking at it for possible enterprise use. Do you think it would scale to that?
Unify, absolutely. And one of their claims to fame, I can't remember. They've actually done a sporting arena. Oops. Actually, it's the demo one. I think Castle Rock. I think it is. That's their sporting arena that they've done. could be wrong. It looks like they've changed some of the demo stuff. But yeah, it definitely scales. So for example, right in this one, this is one of their demo sites. As it maps it out, that's really gross. That's not gonna help. Yeah, they've literally plugged everything into one switch. I don't know why you would do that. But like, if I want to look at devices, oh, that's why. So these are actually meshing routers. Yeah. So they just throw it all together. That's why it looks that gross. But yeah, no, it absolutely will scale to the enterprise level. I think right now, you know, if you go with their little device that I got, this little cloud key thing, I think they limited it like 100 unified devices, so switches, gateway, access points. But you can run this off of a computer, and once you put it on your own computer hardware, I haven't seen anybody actually give a limit.
Gotcha.
I think
so you use their own little appliance, which makes it convenient. You can handle pretty much any level of consumer network,
right,
and probably a lot of enterprise networks.
right. Yep. Yep. Exactly. Yep. And that's where I think software-defined networking is going to really take over, because you know, almost anybody can figure out how to put it together. So
that's cool. Other questions?
Sweet.
All right, Maddie is next, then Alexis.
That's why I did that one stuff, because it's cheaper. If you want, you can go the Meraki route with a Cisco price tag, and you can spend. I think I've spent probably like 40 or 50 grand so far just outfitting 15 access points. One switch. Yeah.
Ready?
Yeah, I think so.
All right.
Okay, so I'm not sure how I'm going to follow Eric. I have talked about cell phone use in the workplace and in the classroom, and my connection to networking with that is just how interconnected we are because of our cell phones and other technology. And this is going to be even more prevalent in the future. So I will talk about cell phones in the classroom and college campuses and the workplace. And I thought that was a good progression, even though that wasn't how I originally planned it. It kind of worked out. So first, cell phone is in primary school or just technology in general. So this is going to be like your kindergartners through 8th graders. In just this past September, Ontario, Canada banned cell phone use in their classrooms, and that brought a lot of this topic back to light about how useful are cell phones. Are they really helping kids learn, or are they harming people or harming our students and how they learn? And so Oxford Learning put out a statistic out there that says kids use cell phones on average of 11 times a day. And I did not grow up with using a cell phone, so that's a lot to me. And just to show that it was in the news, there's a news article. That's not the article I read. But devices can also distract students and really inhibit their learning. And so again, this just raises a lot of questions about whether they are good to have in the classroom or not. And so here's some pros and cons. On the pros side, you can see that there are educational learning apps. When I was a babysitter, parents would have their kids play these apps and they learned a lot from them. So that's definitely a good thing. But other pros are incorporating digital platforms into lessons. So different lesson plans, you can have online resources just to give kids another way to learn. Same thing with supplementing lessons with digital materials, and just the accessibility of the internet and being able to ask Google basically any question and get an answer instantaneously is another pro of using technology in the classroom. But on the other side, you can see kind of what I was saying is that it can be distracting, whether you are the person on a cell phone or a device or not. It can be distracting to the people around you. There are interruptions with notifications. There's a concern about cyberbullying, cheating, obviously, and there's a disconnect if you're staring at a screen, you're not interacting with those around you, which when you're a kid, that's really important to grow those emotional connections and social connections and grow those skill sets. So next, cell phones in secondary school. So this is high school. Another statistic out there, this was a study that I researched, that 50% of teens in the study said that they were addicted to their phone. And then the parents of these kids took a similar survey and they said that they thought 56% of their teens were addicted to their phone. And so again, this raises concern about how phone addiction is really on the rise in this age group. And so in the classroom, or when these students are doing their homework, they're trying to multitask, and that is like that disconnect doesn't help their learning and doesn't help them retain information or work effectively. So again, this impacts how they interact with others face to face, which can cause family dynamic problems. I nannied one family where the two kids were in middle school and they were constantly yelling with their parents about how much phone time they could have, and it was just a big concern for them. And so it more than just on the learning side also impacts family dynamics, and again, children's well-being and their physical, cognitive, social, and emotional development. And so it's just important, even if we know that technology is around and it's going to stay around, but even just to educate parents on the potential dangers that can come with it. And so next, college. I read this really long article about a study performed at the University of Arkansas at Monticello, and there were 4 different groups that were studied. There was a group where cell phones were allowed in the classroom and they were not told that they couldn't use it, so it was just kind of open whatever. There was another group where they could have their cell phone on them, but they weren't allowed to check it. There is a third group where cell phones were removed. They were not in the classroom at all. And then there was a no instruction control group to compare. And so what happened is there were these 4 different groups, and they watched a 20-minute lecture video, which is not very long. It was one of the disclaimers in their conclusion, but it was 20 minutes. And during this 20 minutes, the researchers were sending these cell phones text messages, and they found that it was very distracting, obviously, and that 30% of information is lost when texting during a lecture. And what they found, and then after the 20 minutes, then they had to take a survey, a multiple choice test, and it wasn't even, I don't think it was even on the lecture, it was assessing their level of obsessiveness, nomophobia, and mindfulness. So it was how disconnected they felt from like always having their phone on them and having like the fear of missing out of their friends doing something more fun. And so then another statistic on that was that even if you're not on your phone, 89% of students get distracted in some way during a lecture. So whether that's the person sitting next to you or your phone, it can all be distracting. So it's not just cell phones that can be a distraction. But the conclusion of the study was that students that had their phones removed were the ones that performed the best. So even just having your phone in the same room as you can be distracting. And I think that can be taken into consideration when even we do our homework, not necessarily in class, but just putting it out of the room, out of context, whatever. And one thing that they said in this article is that if a student is texting during class, they're not taking notes. So that's a pretty easy way to show that they're not going to be learning. Next, cell phones in the workplace. So I read two articles on this one because that's kind of where a lot of us are in life right now. And there's not a lot of good things to say, but obviously cell phones are needed and we have them and we need them to communicate with people, which I will talk about on the next screen. But a pro is just increased efficiency and productivity. But the cons are that they can add a lot of anxiety and anger, and this goes along with, or I guess I say that later. This can go along with learning a new technology. So right now at Acuity, we had a lot of new technology roll out last year, and it was a lot for me being a new person, but the people that have been using the same technology for 25 years almost, it's even more new for them. And another con is that managers or even just different companies will give you like a company cell phone and require that you use it and check it often. Even again at my job, we have an iPad where there's certain apps that are automatically on there and we can't delete them. So if you have a cell phone that you're checking all the time and you're getting these notifications on apps that you can't delete, that could be a cause for different anxiety and stress. And it's a way where you can't really turn off work, where if you always have the cell phone, it's like you're always working, you feel obligated to check that notification. And another thing about learning a new technology is that if an employee doesn't view the technology as useful, then they're not going to be very happy about adapting to it. And so information overload is another concern, and a quote that I found on that was that although information overload alone may be stressful, when employees perceive high usefulness, which is the point above that, the effect of information overload on anger may be reduced. Thus, the writer of this article said that he believes that employees' perception of low usefulness with regard to their cell phones may act as a stressor, exacerbating negative emotional responses toward use of their cell phone. So essentially, it's just important to like all of this in consideration. It's important to have training on new technology that you have. So if you are a boss or have any kind of influence on what your underlings are learning about or whatever, then it's important to have some kind of training. So story time. So 56 minutes, that's super like vague right there, but I love this. So in one of these articles, I was reading through and the statistics said that employees use their phone for an average of 56 minutes a day for personal use. If you only work 8 hours a day, that's a lot of your day. And if you have paid lunch, that's a lot of your day. I do not have paid lunch. And so I was really astounded by this. I'm like, 56 minutes, that is a lot of time. And when I kept reading, it said that it wasn't that they were just surfing the web or scrolling through social media. They were actually responding to company emails on their phone. So I thought that was another interesting going along with having a company phone and how it can just get kind of messy with that. So last slide here, going a step farther now, I know that it could be a problem, but we do. It's good to have some kind of company policy. At Acuity, they basically just say, like, try to limit your phone use, make calls during your breaks and whatever. So obviously cell phones, whether they are company cell phones or not, there is a security risk. They're obviously distracting. One policy that you could have is just use your phone for like 2 to 3 minutes max at a time. Obviously keep your phone on silent. I think people generally do that. And it's just impossible to eliminate cell phone use altogether, but parents often need to be in contact with people like babysitters and contractors, and so you can't take it away, but just to be aware is important for people of all statutes. And so that is it. Questions?
Something that's interesting is you said that 56 minutes was the average time people spend on their phone.
Yeah.
I'm guessing that's across like all sorts of different
Yeah.
types of jobs. So I don't know how much time do you think you spend on your phone at work? And
My
what about the
phone?
rest of the class, whether it's work or you know?
Far too much.
On like including my breaks or no?
I don't know. The
I
number's
don't
going to be
think-
bad anyway you cut it for most people, right?
don't
Do you
know.
think you're below or above? Or
Actually
around the
using
56?
my phone, I don't feel like I use it more than like 15 minutes, half an hour at work.
Mm.
But like on my laptop, I can have anything up, and that's not phone.
I got it.
use.
So so the question is does that kind of, is it the same thing?
I
Using
don't
your
think so
laptop?
because it was talking about phones specifically.
I think that computers do the same thing. That's what I should jab you, or that's what I sent in the chat box. I developed picture directory and I just updated it, made it more modern. And people don't know I can do this, but I'm watching the access slots. Some people love to spend gobs of time on there, kind of like Facebook stock and university staff. So it's just like, yeah, it's like I think I invented something that room productivity at university. You're like, I've never knew who that person was. Before you know it, wow, I just
Do you?
I have a question. When you're talking about this question, I was thinking, yes, phone is related to network, but how you think you are probably connected network?
Like
What type of network?
network, like you talked about cell phones and yours.
Well, no. He's asking, like, in general, when we think about our phones, how does that connect to computer networks? I think it does, but tell me how you perceive that it does. I think that's what he's.
Computer, like the Internet of Things and how everything is connected.
What I mean is, so I was imagine. So if you're speaking on cell phone, what do you think about when we don't have cell phone? What distracting us?
What?
You may have.
Oh, it could be like the person that sits next to me at work smacks on his food all day. That's distracting.
When there's no cell phone, students may chatting each other just during class with low voice. And also they may just reading some other entertainment book during class. Or like when you are even you are working in company, you are thinking about something, you're also distracting. I just wondering, this is, I would say, distracting by cell phone is also like we just playing for cell phone. Not really, because cell phone is networking.
So like if the phone wasn't there, what else would?
Or if it's not connected, or if it's not network connected.
So like if you have your phone on airplane mode. I did look at that a little bit. It's still a distraction. Like when you're on an airplane, if you fly ever, like what are the apps that you go on when you don't? Yeah, what are the apps that you go on without network? Like I still play Candy Crush. I don't need a network to be on that. I could spend all day on Candy Crush.
Okay, I just say I don't think your topic is really related to that. It's just.
Well, I don't know. I think access to. Well, so even let's just take the question about if your phone's not connected to the network, how will we use it? I think the way that we commonly use technology today makes the assumption of what that device is capable of. So if our phone's in airplane mode, that's one thing. So if I'm traveling and I have my phone in airplane mode, I pretty much know when I'm going to land. I'm going to have tons of Slack messages and instant text messages, things like that. So even though I wasn't directly connected to it, the time that I was spent traveling, I wasn't, let's say, distracted by whether I used it or not, but that is going to all come back to me as soon as I land and I turn the thing back on. And then I'm going to spend the next 20 minutes in the airport figuring all the stuff that I missed during the thing. So I think part of this is just the idea of being connected to everyone else wherever we are. The phone is our presumed way of doing that, whether it's the phone, whether it's the laptop, whether it's anything else, but we have this assumed capability of these devices. And I mean, the thing that popped up to me when you were first asking the question, I thought you meant is if the phone wasn't there, let's travel back in time before smartphones, what was our distraction then. I mean, there's always been distractions.
Mhm.
So don't we just replace one thing with another thing? So what occurred to me is our cell phones, smartphones, maybe that's the better term, it's just called a smartphone. We're really thinking about the connectivity of it. Are they actually more distracting than things were distracting in the past? I don't know.
Yes.
Okay.
And here's why.
Okay.
I would have loved to do a lot of research on this, but it was like even more sidetracked. And it was like talking about the psychology of like how apps are built how they are like made and built is to be addicting. And that's which I guess kind of goes along with them being distracted, is that not only are they distracted, is that you get on them and you can't get off them. Okay, Seth.
I think there's a two-edged sword. So, I mean, I don't have, like, so when people in this room who have family actually overseas and use passports when they get them, my family lives across the country. So, like, I can't just get on a plane and go see them. I don't even have time to go drive to see them. It takes 3 days. So I really enjoy being able to FaceTime and actually say, like, here are your grandkids.
Right.
Because, like, you know, in the past, like, when that happened, it's like, well, you know, we might write a letter and then we'll dial. So it's nice that, like, we're able to, like, actually connect and have a conversation with people and see them.
Right.
And some of these folks get that very well. And some of these guys over here, because you have to, and I don't have to deal with that. But on the other hand, when I'm at home with my kids, and I notice that, like, my wife and I are chatting with we have small kids, we're chatting with them, and all of a sudden we whip out our phone and start ignoring them because we get a text. It's like, yeah, it's like, this is bad. Because you can see your kids getting mad at you. So.
I'm definitely not saying that technology is not good and useful.
No,
I'm just saying we just need to be aware and like educate parents and educators and even administrators about things that could be happening.
And I do think this is really good. Going back to Dr. Lockhart's 7 big ideas, this is an application of data information. It's an application of computation.
Lots of statistics. All of my articles were statistical analyses.
I didn't grow up going to university when cell phones, smartphones were really a thing. So how do you guys?
The old fart.
Like with your undergrads, do you actually make them turn it off? Or?
Me? No, I don't care. You're paying all this money. If you want to sit here and not pay attention, that's your problem. I'm not a babysitter.
Littman doesn't care. Some other professors will care. I'm trying to think of one that I know that did care though.
I remember there was a story a couple of years ago. There was some prof that you would collect phones at the beginning of class or something like that.
Yeah.
And I don't know, some student was waiting on I don't remember what it was, some medical emergency type call, and it turned into this big thing about whether or not professors were allowed to do that, I guess. I don't know. I mean,
they're doing it in elementary school. They're not allowed to use their phones at William Lutheran.
Correct. Yeah, technically by policy over by us, they're not supposed to. The question then becomes how stringently does that get enforced? I mean, because I'm kind of like you. I mean, they think they're really smart, but when they stare at the crotch for 15 minutes,
yeah,
you know what they're doing. And the thing is they don't really recognize how much time they're actually burning by what it is that they're doing. But yeah, it's a policy that I think needs to be revisited, because it becomes one of those too. I mean, even during Maddie's presentation, I know I've gotten at least one email, probably 2 text messages, and I think Alexis gave me the congratulations on my presentation. She's giving, and the only reason I know that one is because it popped up on my computer too, right? Which then also distracted me, and I missed the first 30 seconds or so of the 56 minutes of usage time.
Without it even being your fault, it was you had a device that was connected, and it just beeps and buzzes, and now we all have these smartwatches, which is really an extension of it. So, I mean, the whole reason I got this watch when I switched from iPhone to Android is I don't get notifications as like conveniently on Android. They don't stay persistent. I've kind of made it so it's better now, but so I don't like wearing a watch otherwise, but this lets me get all my Slack messages, and you can imagine how many messages I get per day on those things. So it's like, It's constantly buzzing. I'm sitting in chapel this morning and my watch is blowing up. You're kind of peeking down, you're like mid prayer, kind of seeing what's going on.
Relatable.
That's fine, I get them anyways. You won't be alone.
So I had a question for you,
I think
man.
Alexis has a question, but do we want, let's have her, because she's next.
Right.
Let's have her when she sets up, she can ask her question at the beginning, so then she'll be on audio. And then Ishtiak is next.
Alexis, you can share your screen now.
Huh? No? Oh, you
So my question for you, Maddie, can you hear me?
volunteering to be next after him? Okay. Since I haven't rolled the number yet.
Can you guys hear me?
Yes.
Okay, so Maddie, my question for you is, so like you were talking about how like they banned the phones and stuff for like the elementary school kids and like maybe some high schools and stuff, but wouldn't laptops be a distraction as well? Because they can still do a lot of the stuff that you can do on phones today on a laptop. Yes. Yeah. Okay. So do you think that they should be banning like laptops as well? I know like some places like have their Wi-Fi where they like, I know like Concordia, like they block like certain websites and stuff on their Wi-Fi so you can't view certain things. It's like I know some schools, like I know my high school, even when I was there, they had stuff pretty locked down, but like there's always those, like they can't block everything. So I guess just like, what's your opinion on like how they could improve that?
Okay. I would like to speak. Can I interrupt you 1 minute?
Was it dealing with my question or like, because I would like an answer.
Question. I think is using technology in right time, right thing is good. And when a student goes to the class and using his phone or iPad or computer, if it's he's using for research purpose or educational purpose, that's good. But if he's doing different other apart from the subject, apart from the class assignment or something, if he's using the net and it's iPhone for the just like Facebook or some other thing, that's wrong. I that's my thought.
What's your thought on that, Maddie? Hello?
I think she can't hear.
They might have turned the speaker off on Littman's computer or
Yeah.
something.
All right, now you can hear us.
Okay, so for like the 5th time, I said I have teacher friends that teach middle school that have a way to only allow Google Drive on their Chromebooks, on the students' Chromebooks. And so I can see something like that being implemented. And even when I took computer science in high school, my teacher could see exactly what we were doing on all of our screens and could control our computers if they were not acceptable. So
I think people maybe are just unaware of the technology that's out there for that and not implementing it in schools when maybe they should. But yeah, it's not, we can't take away all technology necessarily unless you want to do, what's it called? I'm looking at you because you're saying no, but classical education. Unless we're going back to that.
And I can check on that a little bit too, right? Because when you look at the laptop in the classroom, I think the difference is screen size. And so for a teacher who actually is policing a classroom, it becomes easier for them to keep an eye on what it is that students are doing. You know, some students like to think they're clever because they can, you know, alt tab between active windows and things like that. But if you're actually paying attention, in addition to being able to implement tools like, you know, screen sharing or classroom management tools that way, you also have the ability of just being able to walk around. You know, the difference between that and the cell phone is, you know, economies of scale. You know, with the cell phone, you get buzz. You know, you click the button, the screen turns on, you see the notification, you respond to the notification, click the button again, you know, your computer's off. That's kind of where I see the difference between those two devices. Although I definitely agree with you, I think that's going to be a frontier that educators are going to have to take a look at relatively soon.
Yeah, I think my high school did have something like that too. Like, if I remember correctly, I think in our computer lab, like on those computers, they were school computers. They literally had a system where they could view every single person's screen.
Yep, I do too.
Yeah. Okay. Are you guys ready?
Yep. So let's see. Maddie needs. This is Alexis's already. I was thinking it was your presentation.
Nope.
Yeah. Give me 1 second. Well, give me like 4 seconds. Okay. I'm ready whenever you are.
Okay.
All right, everybody shut up so we can hear it. So your only way of hearing this is through my speakers.
Okay.
Go.
So I decided to do my topic on neural networks. Just the past couple of years, I've been really interested in artificial intelligence, and that's a huge part of that. So I guess, like, first off, like, what are they? So neural networks are like brain-inspired systems intended to replicate the way a human being thinks and learns. They also have 3 layers: an input layer, an output layer, and then a hidden layer that transforms the input into something that the output layer can use. They are a great tool for finding patterns that are too complex for a human programmer to solve. And they are also called perceptrons and have been around since actually the 1940s. But just recently, in the past couple decades, became a huge part of artificial intelligence. And then there are many different neural network architecture types, such as the single layer perceptron, radial basis network, multi-layer perceptron, recurrent neural networks, long short-term memory recurrent neural networks, Hopfield networks, and Boltzmann machine networks. And the hardware architecture for neural networks includes software simulation and conventional computers, and special hardware solutions for decreasing the execution time. And then the different types of training algorithms for artificial neural networks are the gradient descent algorithm and backpropagation algorithm, which I'll talk about a little bit later on. And then there's different types of learning sets, which we kind of did some of this last semester for those of you that were in the class. We had created like a machine learning project where we had to do a training data set. So like that's just one of the sets is training data set. Then there's the validation set approach. And then there's also the test set. So like last semester we had the training set and then the test set. So we trained our machine with the training set and then tested to see its accuracy with the test set. And then there are 5 algorithms to train a neural network. And that's being the Hebbian learning rules self-organizing component rule, and then the Hatfield network law, and the LMS algorithm, as well as competitive learning. So like I said, they made it kind of based off of like a human brain. So I guess kind of how does a human brain work is a question as well. But artificial neural networks include neurons, which are like the biological neurons in our brain, which are also called nerve cells. They are fundamental units of the brain and nervous system that receives sensory input from the external world. So using dendrites, they process the information and give an output through the axons. The cell body or soma contains the nucleus and carries out the biochemical transformation necessary for the neurons. And dendrites are hair-like tubular structures on each neuron and accept incoming signals. The axon is a tubular structure that works like a transmission line. The synapse is where the neurons are connected to one another in a complex spatial arrangement, where the axon reaches its destination and then it branches again, and this is called terminal aberration. And then the synapses are at the end of the axon and connects to the other neurons, so connecting them all together. The dendrites then receive this input from the synapses, and other neurons then can pass it on. And it processes the soma, it processes the incoming signals and converts them into an output, which is then sent to other neurons through the axon and the synapses. So artificial neural networks kind of work the same way by having the input layer, having the hidden layer in the middle, which is doing what it needs to do, and then passing it to the output. And then differences between the human brain and a computer. Our brains have biological neurons or nerve cells. We have 200 billion neurons and 32 trillion interconnections. Our energy consumption is 6 to 10 joules per operation per second, and we have the learning capability. But computers have silicon transistors, 1 billion bytes of RAM, and they also have energy consumption of 10 to 16 joules per operation per second and a programming capability. They are similar though in the fact that neural networks are meant to resemble the human brain. So the following two ways that is that we both acquire knowledge through learning, and a neural network's knowledge is stored with an interneuron connection strength known as the synaptic weights. Oops, wrong way. So deep learning is a powerful branch of machine learning, which is a technique of teaching a computer to do things that come naturally to humans, like learning. This is a huge key behind driverless cars, such as showing them when to stop and go and the difference between a pedestrian and a lamppost. This is going to be a huge key in voice control as well, and phones, tablets, TVs, hand-free speakers, and much more. Deep learning models can be used for many complex tasks, and that's where the neural networks come in. And those complex tasks include artificial neural networks, which is used for regression and classification, convolution neural networks for computer vision. This is a type of neural network that captures more complex features within its input data. They're constructed with a sequence of layers, such as the convolutional layer, the max pooling layer, and the fully connected layer. It then computes the dot product between them. The convolutional layer is extracting the features from the input layer or input data, and then the multiple convolutional layers are used within the same network to allow it to learn more complex features as the data is propagated. The pooling layer then reduces the spatial size of the features. This decreases the computational power required to process the data using dimensionality reduction. And the two types of pooling layers that are used are max pooling and average pooling. And then fully connected layers take the flattened vector representation of the convolutional layer and pooling layers and classifies the data, the input data, and then outputs this as a one-dimensional vector that represents the probabilities of the input data belonging to a certain class. So they're just other fancy ways of saying input, the hidden and the output. And then there's also the recurrent neural networks. So this is good for time series analysis, and this allows the data to flow in multiple directions. These also process a larger learning ability and are used for more complex tasks such as learning handwriting or language recognition. And they deal with sequencing problems. A problem where the data is fed into the network represents a sequence. Some examples include day-to-day air temperatures, closing prices of an individual stock, and then many more. And recurrent neural networks introduce feedback loops into the network's architecture, allowing them to use information from previous calculations in order to determine a new output. This gives them a memory-like capability, which allows them to look back a few steps dealing with sequential data. Then there's also self-organizing maps for feature extraction, the deep Boltzmann machines for recommendation systems. These networks are similar to the Hopfield network, except some neurons are input while others are hidden in nature. And the weights are initialized randomly and learned through a backpropagation algorithm. And then there's also the auto encoders for recommendation systems as well. So there's also this thing called the activation function. So activation function is important for the artificial neural networks to learn and make sense of things that are very complicated. The main purpose is to convert an input signal or of a node to an output signal. This output signal is then used in the next layer in the stack. Types of activation functions include threshold activation function, sigmoid activation function, hyperbolic tangent function, and rectified linear units. The two most common activation functions, though, are with binary and sigmoidal hyperbolic. As you all know, binary is ones and zeros, so it looks at the net weight, and if the net weight is input is greater than 1 and output is assumed 1, otherwise it's a 0. And the sigmoidal hyperbolic is an S-shaped curve. The hyperbolic function is used to approximate the output from the net input. So you probably heard me say backpropagation quite a few times. So this is used, it's applied continuously through the network until the error value is kept at a minimum. In backpropagation, there are two ways to adjust weights: brute force method and batch gradient descent. Brute force method is best suited for single layer feed. For networks, you take the number of possible weights, you eliminate all the weights except for the one right at the bottom of the U-shaped curve, and then the optimal weight can be found using a simple elimination technique. And then there are the batch gradient descent methods, which it is a first order intuitive optimization algorithm. It finds the minimum cost value in the process of training the model with different weights and updating weights. And then there's also the stochastic gradient descent method, which this looks at a few samples that are randomly picked from the whole data set instead of using that whole data set for each iteration. So my conclusion is recurrent neural networks and long short-term memory networks enable complex time series. Our forecasting are focused on predicting parameters in the future by referencing parameters from the past. Bitcoin actually uses this by looking at their price points. Recurrent neural networks can be trained in order to estimate its future price, and this is being used in blockchain more and more. And neural networks are also basically the future of AI, and they are the new concept that has just scratched the surface, and they will most likely be used for many different concepts. So that's something that is never really going to go away. And as we learn more and more about our human brains in the medical fields, we'll be able to make neural networks be more and more like how human beings learn as well. Any questions?
All right, if you're going to have a question, make sure you speak up. Nothing? We got nothing?
Do you think there's a limitation that's going to be reached from a hardware perspective versus our human minds?
I mean, honestly, it's really hard to tell because like we really don't know much about our human minds. Like we're learning more and more every day, just like we're learning more and more about technology every day. And technology, like kind of like you guys were talking about 5G and 6G before, like we're always improving on our speeds and everything. Can there be a limitation? Yeah. Do I think it's going to happen soon? Probably not, because we are still developing a lot, and I feel like as human beings we could go a lot further. And the fact that our brains are the ones creating all this technology, I feel like it's really it's really going to be kind of like going in like a merry-go-round. Like we might have a limitation, but we might be able to solve it because we're passing the limitations of our human brain, and we'll keep passing those limitations, if that makes any sense.
Yeah. So then I guess the next question becomes, is this forecasted to replace what the solid state drive or the central processing units?
I'm not really sure. I didn't read anything about that. I think we're still like in the like newborn stage of neural networks and artificial intelligence. Like, yeah, I think the biggest place it's being used right now is in like smart devices and like face recognition and some small robotic stuff and self-driving cars. But I guess if we can really somehow, because I feel like, I guess I kind of feel like we, like artificial intelligence and neural networks kind of need that backing of the storage and the CPU. So I don't know if it would technically replace it as so much need it, but I guess it could always somehow get combined and it could end up somehow powering itself, but I really don't know.
Okay. It'll just be interesting to kind of see, because you were talking about how, our synapses store the data in between. I was just curious as to if the hardware is to the point where it can.
At what point is it better than our brains?
Yeah.
Yeah.
Yeah, no, that's kind of why I picked this topic, is because I just find it so interesting, because like artificial intelligence in general is like trying to mimic like how the human brain thinks and acts, but like the fact that we don't even know everything about the human brain, it just like it was just really interesting on that. And yeah, I agree. Like we could get to that point where, like, because we're basically self-powering ourselves, so I could see it possibly happening.
It's actually bigger than that. I mean, you said that we don't know everything about the human brain. We actually relatively know very little about the human brain.
Exactly.
Most of our modern neural networks are actually based off of like insect and cat brains and things like that. Things that are far less complex that we understand better. So I think maybe with the advent of quantum computing and with the assumption that we're going to keep learning more and more and more about how the brain works, being able to create a computer model of it maybe gets more powerful, but I don't think it's just about the hardware. I think it's also about the how. You know? And but then it actually becomes fairly interesting from a Christian point of view as you think about how much of the brain is God created in terms of beyond our understanding versus like, can we mimic that in a computer program, or is it something more mysterious, I guess. So I've always found neural networks pretty fascinating. All right, other questions? All right, so we have Ishtiaq next, and then Priscilla. Well, we have you mean the human genome? Yeah. Yeah, I mean, that's different than how the brain works. And the genome is how our whole DNA sequence. So that would be being able to represent a human in bits or something like that if we wanted to. And the amount of data, at some point I remember I heard the amount of data it's big to represent the whole genome. But yeah, that's different than how the brain works. You're fine. I just was getting the microphone a little closer to you.
Okay. It's like, hello all. So my topic is wireless sensor networks. So I choose this topic because it's the most researched topic in the last decade. And also it has a market forecast of like $2 billion and estimated in 2020. And it's very much related to the Internet of Things. So that's the reason I chose wireless sensor networks. And we are using many types of sensors nowadays. So first of all, what is wireless sensor network? So wireless sensor network is just a sensor, and it's a tiny device that has sensor nodes that communicates with the gateway, and we all know that the appropriate and the most suitable gateway is the internet. So then the data is then passed to the sink, which is a kind of local user, and which then uses the data locally and connected to the internet. So here is an example of the ZigBee processor, which has like, I have to explain the components of it. So first of all, like a processor, we have for like advanced components. It has processor, it has a radio interface which gives the radio signals to it, and it has an analog to digital converter, which actually takes the sensor have to go with it to sense the things like temperature, humidity, and human temperature, human body temperature, or the pulse rate, or any kind of things. So it actually converts the analog data and convert into digital, and shares the data with that. And it also uses memory because like the sensor has a very much low amount of power source, so it also uses batteries for it and also uses memory for it. So communication models for the ZigBee model is like the standard it uses is IEEE 802.1.15.4. It also uses GPA Bluetooth for like personal area networks, which is like limited areas or which is very nearby devices like smartwatches and the things which are near to us like home network and things all. And it's also like identical to Bluetooth is or the limited area is the Wi-Fi connection, and for somewhat a large area we use GPRS and 3G connections so as to locate the on traffic analysis with that, and also tracking where you are and or we have to go to the destination from source to destination in some amount of time and all. So there are different kinds of wireless sensor networks. So first of all, the terrestrial wireless sensor networks where so first of all, like the wireless sensor network has a deployment of two types. First of all is a pre-planned manner type, which we planned already, and to have that kind of sensors to be planted or to be placed in certain locations within a certain area. And it has another kind of deployment called as ad hoc deployment, which is a wireless connection. So in the terrestrial wireless sensor network, we actually plant these sensor nodes from an aeroplane, and it is called as an ad hoc network. So it's actually based on the wireless connection that actually reports the data back to the base station. So in that, like what the things the sensor nodes are planted fall off from the airplane, and in that, like sensing the terrestrial wireless sensor networks, like finding a way into the amount of space and kind of that things. So, but like we have to store the energy, and the limited energy is available on the power source. So that the thing is like we have to use solar cells for it, and we are implementing it more. The other kind of sensor is we can find is underground sensor, in which it deployed in a kind of pre-planned manner, and it like they all used to buried under the ground in like caves and mines, and it has the same nodes, and that's a base link that you have seen in the picture, and that it senses all this information collected and sends to the base station. And regarding that, we can include some of the tracking of monitoring, like underground monitoring lights, the amount of minerals, waters, rocky areas, and some sort of things like by digging the portion where we can find the water, underground water, and where we can find the rocky soils and all of that kind of things. And the next one is the underwater wireless sensor networks. In here, the same, it's here where the sensor nodes are placed statically and onto the very much deep level. So the communication within this will be not much accurate, we can say. So what they do is the substations, which we are seeing in the picture with the yellow colors are pointing them. It's kind of robots. They used to float into the water and goes near to the static nodes and find out some information for every amount of instruction cycles or for every amount of responding time. So they will gather the information and passing over to the every static station that has been deployed into the underwater. And they used to track and monitor the marine stations, which will go underwater and the underwater ocean environments and some technical issues, natural disaster issues like cyclones and tsunamis and that kind of all type of pollution monitoring, etc. And the next one is the multimedia wireless sensor networks, in which we uses like camera and microphones as a main cause for like detecting any kind of security threats that used to be happen. Like if you are saying that we have to capture the video, if you like break the signal, and we in India there is used to have a system like if you break the signal, we used to get a snapshot of it and we'll get posted to the home with a picture. So this kind of like wireless sensor network is based on it. Like if we sense if the sensor it is in the limited area region, and if the cross signal it will detect the sensor with the amount of user time. And here also where if we speed limit more than 30, that kind of things. So the police came back and so it uses the kind of sensor, the sound waves and the traveling waves that has been detected by the sensor, and it reports to the base station, and if it don't, they know that, and they will come to you. The other is the mobile wireless sensor networks, in which like they use mobile sensors for mobility purposes, and the sense anything that we can say as a search and rescue system. And the target tracking of the enemy tracking, if any person is looking, if there is any kind of person that has been we are tracking about, so we can find a way onto him. So this kind of sensor also used like mobile sensor networks to actually sense any dangers with the person that is actually causing any harm to our society or environment. So some of the application areas I have think about wireless sensor networks is the main one is we are using nowadays like wireless body area network. It is a short range wireless network comprised of devices actually positioned within the body, and to monitor the pulse rate and to monitor how much steps we walk and how much heartbeat of the patients in the hospital, and what are the critical conditions and what kind of disease it has been showed to them by using the amount of sensors. So it is basically not only the patient's monitoring in the body area network, it also like security purposes. Like for example, if you're using fingerprint sensor in your phone, so what is kind of it senses the amount of fingerprint, and it actually tracks and monitors and gives the accurate, and then it unlocks up. So it basically not only patients monitoring, we can say, or the health benefits we have, we also have body area network as a security purpose. And the other one I have researched about the application is pin PTR, in which it's a kind of to locate the shooters with the sound waves of the bullet that is being shooted with from the gunfire. So if sound originates So this kind of with the, how much speed and how much intensity, so the kind of sensor that has been implanted around it, so it actually reports to the base station, and we know how many soldiers are there and any cause of danger happening or not, and we are connected to them through wireless sensor networks. And the another application I've read about is like a Zebra Net, where we used to track animal migrations and all kinds of animal movements during day and night. So we can see the geographical area of animal planet. All we used to track animals like how they used to eat and drink and all kinds of animal habitat inside the oceans and inside maybe on the underground, basically in the wildlife like safari, and going to the safari and taking the videos and shooting them, and how kind of foods they eat and what is their natural living habitats on them. So what they're doing is like an exam in the picture displayed as like they're tying a collar on the neck of the animals, and they used to have what kind of fear the animal has. So they will sense, and then the other when the fear comes to the animal, like someone is chasing them for eating, for like killing an animal and eating the other animal. So that kind of sensor it can be used, it can be sensed by the collar, and they will know that this time of attack there will be fight between two animals, and the person the animal will be like going to the home, sleeping, and what they are doing. All the monitoring, we can say the animal movement monitoring has been implanted with the wireless sensor networks. And also environmental monitoring. I have researched about like volcano monitoring. It has happened in the northern equator on a mountain called it's a volcano Reventador mountain in northern equator. So he planted in a pre-planned manner. The deployment has been placed in a pre-planned manner in which 16 sensor nodes around the area of like 3 kilometers have been deployed, and they have searched throughout, and they can, like sensor, we know that the sensors can sense humidity, temperature, and all kind of things. So when the amount of eruption causes to some level, they will use to know, and that kind of sensor to the stations, and the mountain is like so they have planted like. So they can know the amount of eruption that will cause very near, and they can sense the danger, and they can monitor it. And many of the earthquakes happen in around our world, so they used to detecting and posted them for as well. So another article was I was reading is the wireless LANs, in which we connected to the system through wireless networking, and because they are more becoming popular, and it offers many advantages over like fast and simple installation and flexibility and scalability and many kind of things that are used in wireless LANs, and which is a kind of wireless sensor networks. So basically networking is a kind of wireless sensor networks. And we got the types of wireless LANs, which is wireless personal area network, which is the short range devices that I told you in the starting, like it is used for the short range communication. Example, we can use it as a smart homes, and we are using some smart watches and Bluetooth kind of devices. So it considers this all examples in under wireless person area network. And in wireless LAN, it basically on a limited area region, we have seen the example of like some kind of animals. As a branded example is a kind of or the offices or the buildings we are using in all is a like a wireless LAN connection. And wireless LAN connection is like metropolitan, like connected to some miles area and some geographical area. So we track some kind of information and through the wireless metropolitan network. And basically the last one is the wide area network, in which many kinds of networks attached to it are becoming more popular, like 2G, 3G, and 4G. And 60 is also on the way. So, but another article was I was read about like security threats for the wireless LANs, and it has two types of attacks, because we know that the data will be transferred in through the air, so it is like insecure. So that's the reason many types of security threats have been happening for the wireless LANs connections. So first one, there are two types of attacks, like passive attack and active attack. And how gonna be like, what are the threats that we are just only talking about? Like the passive attack comes under like eavesdropping, and someone listens to your communication, and maybe they come to you and they do everything as a type of authorized user. So that comes under masquerading. And traffic analysis is the other one where it will monitor very intelligently about your the things that are like I showed all the things that are in your network. It is analysis. So what he can do is the threats has like it will do very intelligently that it doesn't feel that you are using your it implements or impersonates the person like you are using only. So that's kind of things are the attacks of wireless LANs. And the other one is the message modification, where everyone, the person used to come in the network and delete it or maybe change the message. And everyone we know is a denial of service, where everything prohibits as the normal user, and we cannot do the things which we want to do. So these are this is my end. Thank you.
All right, that was almost 17 minutes. All right, so any questions?
One of the articles I was reading about reminded is I thought I was going to present on PKI, which is how we do SSL. Communication basically is how we can encrypt data when it transmits. So they talked about for the Internet of Things like sensors, they need to talk back and forth how we could use blockchain to come up with a new, well, without getting too into it, for coming up with a new form of PKI, because they talked about that. The way it works right now is you get a certificate, but it's only good for a certain amount of time, maybe 1 year, 3 years. And so you can encrypt your traffic for that amount of time, but you have to get a new one. But when you have millions of sensors, you can't do that. You can't go around certificates on each of them like that. So they talked about like how maybe they could come up with PKI that relies on blockchain for validating the authenticity of the certificate to mitigate against the attacks you were referencing at the end.
Yeah.
So it was an interesting presentation. My wife's grandma is 102 years old, and she lived, that's I keep telling her, honey, you're gonna live way longer than me. But it's very good genes. But she lives in her house still. But someone has to be there all the time to like watch her, so they pay like a nurse to sleep in the house. And I thought it would be interesting with like WSNs if they could come up with a sensor network, because my in-laws, so my wife's parents live next door to her grandma. If they had like some sort of WSN alarm system that was in the house that could like trigger like when grandma needs help, because it only takes them 30 seconds to get over to where she is.
Yeah.
That would save
Rather than life alert.
Well, this woman, like she can't do any of that stuff, you know, the dementia's taking hold, so she's doing a lot of that stuff. Although I don't know what life alert is, Maggie, I'm pretending. What is that? Is that the one that like,
You push the button, I've fallen, I can't get up.
Yeah, no, she couldn't do that anymore. So we need like a sensor.
Do they come with sensors everywhere?
There's a thing you install at the like a base station at the house, and then there's like a necklace the
I know the
person.
necklace part, but are they getting smarter? Like maybe they do or know how to detect a fall.
At least the one my grandma has does not. And I think she has one
Future of
from
technology,
4 or
right?
5 years ago. All right, let's keep trucking.
Keep removing.
So we got Priscilla up next, and then Galib.
He's gonna be West Band.
I know.
April 20.
I wish their parents knew who he was. I wish their parents knew who he was because I laughed. Oh my goodness, best correlation ever. I also
There we go.
And you have your audio unmuted.
Yes.
Or no, he's the younger one. What's the guy?
No.
I really wish you would change next talk, Professor.
Two.
Anything.
What's the current topic?
I am changing my topics a little bit, but I will pretend they are.
The next one's computer architecture.
Yeah, that's a good one. Well, sometimes, like for instance, a couple people messaged me during this one. If you came up with a cool topic that was, let's call it, loosely connected to the topic of the week, and you ask me about it, then usually I'll say yes, that's fine. So.
I'm gonna do this for
Gonna
next
have to
one.
move this.
So don't purposely do something not related to computer architecture, but if you happen to stumble upon something interesting as part of that, then.
Trust me, I already tried to start computer architecture and I can't.
So today I'm going to talk about a different kind of networking, the networking between industries. And I will talk about how data science industry can help to solve real problems. In this case, helping the pharmacy industry to solve a national crisis, the opioid epidemic. I'm sure you guys haven't heard about the opioid epidemic. Who here is not here about at all? Does anyone? Okay, I will go over what is the opioid epidemic about. So just to know if I should skip some things here and there, but also, there's anyone here that works with data science? Predictions? What?
Yeah, we have a data warehouse, and so I don't know what predictive algorithms we have yet, but we're really good at doing like regression analysis on historical data.
Okay.
So yeah, but like I'm the database administrator. I give them the data. I don't analyze the data. I know what they do with it.
Yeah.
The example was predicting very well.
So for example,
I pause your time.
Yeah, what they want to know is like they want to like take a look at historical records of certain kinds of students and like how well did they succeed in the past, and they might extrapolate that out into the future with a regression analysis to say we have a student and they meet these conditions and we think they're going to struggle with their studies in Concordia, so we're going to try to help them. And so they look at the data sets in the database and try to identify people that way.
So by the end of this presentation, we're gonna show some solutions of where the data science exactly can help with the opioid crisis and using also some regression analysis. So today I will talk about what are opioids for those who don't understand or haven't heard yet about the opioids crisis. We're going to talk about that too. We're going to compare some solutions. So it's not just a national crisis, it's a world crisis. So I'm going to show you a comparison with other countries, what they're doing, one other country. And what is being doing in the United States nowadays. So what are opioids? Opioids are prescriptive drugs that interact with opioid receptors in your brain, and they're painkillers, and they are prescribed by doctors every single day. And they can create a feeling of euphoria or make you high if misused. Those are some remember some names here. So what is the opioid crisis? Now we have some catastrophic data that we can analyze about this epidemic. And since 2007, it was seen before that, but since 2007, the data is massively being analyzed around those prescriptions and how people are using those drugs nowadays. And we know that 21 to 29% of patients prescribed opioids for chronic pain, and they misuse them. And we're going to talk about what is considered a misuse person. Between 8 and 12% develop an opioid use disorder. 4 to 6% who misuse prescription opioids transition to heroin. And about 80% of people who use heroin first misuse prescription opioids. So if you think about how heroin is destructive, and thinking about that almost everybody that is addicted nowadays started with opioid, and then you can realize how critical it is. And the fun fact, not very fun, about Midwestern. Here in Midwestern, saw opioid overdose increase 70% from 2016 through 2017. So what is considered misuse of opioids? Opioids, those painkillers, they're mostly prescribed after surgery or for chronic pain, or even patients that are treating cancer. So they're very strong medicine that is used for as a painkiller. And what's considered misuse? Taking too much medicine, for example, if your doctor prescribes you 2 pills and then you take 4 because they make you sleep good, and then you think, I'm gonna sleep better if I take 4. It's not gonna be a big deal. There's a misuse. Taking someone else's medicine, it's very common. Before we have all this control on the opioids, you could prescribe someone more pills that the person actually would need. And then after the surgery, for example, after a person uses the pills that they need, the leftovers would stay there, and you can just keep in some cabinet in your house, and anytime anyone would need a painkiller, they could just go to that painkiller without knowing how strong it is. Taken in a different way than you're supposed to. So for example, if your doctor prescribes you 1 pill every 8 hours, and you decide to take every 6 hours because you think it's not, by the end if you're starting to feel the pain again, so you just start taking every 6 hours. Or if you, for example, if you're going to sleep and you're gonna sleep, so I'm supposed to take this every 6 hours, but I'm gonna sleep for 10 hours, so I'm just gonna take more here since I'm not gonna take all the pills there. So these are all conceptions of misuse. And of course, taking the medicine to get high. What can you do to prevent opioid misuse? And all of this, it's about the same, and it is information, knowing about it, talking about it, and actually getting to understand what those drugs are used for. Question your doctor if there's any other step medicine or any other option that you could take instead of this strong drugs. How did opioid addiction begin? And my first talk here is teaching people that pain is bad and that you have the right to not be in pain. It's not a bad thing to not treat pain, but to contain pain. I'm not saying that people shouldn't take painkillers and that you should suffer, but the conception of how much pain a person can take was massively attacked with marketing in order to sell those painkillers. So the measurement of pain and how much you need medicine for that it was being huge misunderstanding the past years. Small studies from pharmaceutical companies claiming that these painkillers were safe. So this small studies go again with the lack of research. There's no studies enough when in the 90s they started just selling producing the opioid painkillers, but they were being sold as they were safe. There's no studies about that. And again, lots of money injected in the industry and a lot of marketing to sell those. So here I will bring you some data about another country that had the same issue that the US is having nowadays. So the US is nowadays, United States is the country who has the most percent of population addicted to opioids. The second is Canada, and the third is Germany. In Germany, in 2016, they had the same amount of opioid prescription and same rate of opioid addiction, and they are still selling the same amount of drugs. They're still producing the same amount of drugs. What is different is how they are fighting the opioid user disorder without fighting the industry. The industry is powerful, and this is the main rock in the way to solve this problem, is how powerful the industry is. So first thing that Germany has different from the United States, it's obviously the healthcare system. It's affordable for someone who has a chronic pain or something like that to go more often to the doctor. So in general, doctors can watch closely each case. So this is the point. Data screen. There are some data screen process that is some analysis based on the patient conditions to see if they should prescribe opioid or not. And this comes to data analysis because based on all the patient past conditions, you can predict who is more prone to become an addicted person and who is not. So it's safer to, for example, to predict some opioid painkillers to a person than to another person. And they can know that based on those factors. And the very non-traditional topic that are the safe injection sites, which are places where addicted people can safely go and take their drugs being watched by doctors. So it's a very controversial topic, but it's saving life in Germany, and all the information being actually in the whole Europe is like that. They talk very openly about addictions, and they teach people that are addicted how you should just use a clean needle and take small doses. They're not telling people don't use drugs. They're telling, do you want to use drugs? It's your choice, but do it the right way. Start with small doses and never take them alone and things like that. And since then, the addiction rate in Germany is still flat, even though they're still selling the same amount of opioids. And while the scenario increased 30% from July 2016 through September 2017 in the US. So how is the United States facing the problem? The United States is facing the problem without fighting with the industry. But this is another political issue that I'm not going to talk in this presentation. So they're expanding access through health centers and other primary cares, using telehealth to treat opioid use disorders, connecting stakeholders to opioid-related resource. And this means opening their database. Now the industry is watching those data. I mentioned in the last presentation about how health insurance are allowed to send to companies the data about who is taking opioids in their company, and the government wants to know that. So we are requested to send the government some data about how opioids are being prescribed, who is taking the prescriptions, how many times a year a person is prescribed with opioids, where these prescriptions are coming from. And with this kind of data, we can find, for example, 3,000 inhabitants, small town in Ohio, where there are 1,000 prescriptions per month of opioids. This is something wrong there. And of course, there are a lot of not just misuse, but also the drug dealer industry is very smart. So now sharing this data, it's been possible for the government to watch closer to those cases. Informing policy and future investments. There are massive investment in the opioid situation, and addressing opioid-related poisonings and overdose, again, sharing data. So how is the United States using data analysis to solve the problem? The FDA is creating a large-scale data warehouse that will improve the data analysis. And the plan is to utilize this data and implement new policies and enhance research and innovations. So there are other things like the US opioid prescribing rate maps, which are exactly what I just talked about, where you can map where people are prescribing more opioids and match like with the population and rates like that. Opioid guideline apps that are apps that can control the dosage of morphine in not control, but they can tell the prescriber the dose of morphine and opioids so they can access quickly and match with other medications. And this is something very interesting because we're talking about things that were not being done 3 years ago, like analyzing what other prescriptions were you taking and if those prescriptions match with the dosage. So the morphine in this prescription matches with the morphine in this other painkiller that you're taking. And it's crazy to think that doctors don't have this information as easy as we think that they have. So we have to provide them this information in a way that they can access quickly and easily to prescribe their medication. CMS Medicare Part D opioid drug mapping tool. It's also the drug mapping for, so we can see which states people are, not the states, but like the rates that people are taking more prescriptions per year, where people used to take, refill their prescriptions. This is very important to because sometimes you do a prescription here in Wisconsin, and the person will refill the prescription in another state. And if you don't map all this information, you can have people misusing drugs. And also overdose, another software that does those overdose statistic, because we need to know who is dying and what they're taking while they're dying. When a patient has an overdose, if this person is an addicted, usually to higher drugs like heroin, it's difficult to know if they're also taking opioids or if they started taking opioids. So this whole analysis of how this person got to the point to the overdose is also being analyzed now. And the morphine milligram equivalence, the MMA, that's another software that does this dosage analysis. And where is Milwaukee in this scenario? In 2018, we had 305 opioid-related deaths in Milwaukee. And even though with all the since 2018, people are talking about the opioid crisis, and this number was supposed to decrease, but it's not happening. So in 2019, we had 327 opioid-related deaths and 800 opioid-related emergency room visits. So the death caused by opioid overdose could be higher.
We're currently at 20 minutes.
So just another, I'll have just, Milwaukee just we're having a lawsuit. They're suing companies, they're manufacturer companies for the opioids, and Milwaukee was the latest city to file the lawsuit. And also I found an article this past week about the Northwestern Mutual Data Science Institute that will launch a project in February that will use public data from local sources and do special analysis to study opioid overdose here in Milwaukee. Any questions?
So now, well, first of all, it is a really interesting topic, and let me kind of close a couple of gaps maybe. So I think it is really connected to the idea of computer networks, actually. So I can use my own experience as an example. So, and I also have friends who do this. So I have, you go to a doctor, the doctors need, they're under a lot of pressure not to prescribe certain medicines because of this epidemic. But they don't necessarily know who might be an abuser, who actually needs the drugs versus who doesn't have the drugs. Then you go to the pharmacist. The pharmacist, they might not be on the same systems as the doctors are on. So you need to have those two systems talking to each other so you know which patients are at risk, which ones aren't. Well, now you have some patients, let's call them the addicts, who will go see 3 or 4 different doctors, go to 3 or 4 different pharmacies, and get 3 or 4 different prescriptions from these different doctors at different pharmacies, none of which historically have talked to each other. So now all these things need to pool together with some sort of centralized database or at least a check and balance system. So we can say that from a prevention perspective, that's a positive thing. But now you have the flip side of the coin. What about the people who do need the drugs and they can't get the drugs? Because I think now we have and that's why I found the Germany thing pretty interesting here with the some of their approaches to it. You said that it's not a growing problem; it's a flat problem at this point, where it's just maintaining. Yeah, and I kind of like the idea of like the centralized, safe injection locations, because I kind of think about like when I had my knee surgery earlier this year. So I mean, I'm pretty anti-pain meds unless stuff is really bad. So anytime I've been prescribed opioids. I only take it, you know, the doctor gives you like 12 pills. I take 2 of them or something until, you know, I don't need it anymore, because then you don't want to get hooked on to something like that. But in that particular case, the guy who did my knee surgery was very, must have gotten burned at some point. So he was very careful about what he would prescribe. So he does knee surgery on a 400-pound guy and prescribed me Tylenol with codeine. Well, that's not going to cut it. So, and I told him, based on my own experience, Percocet is something that works for me, wouldn't prescribe it. By the time I finally got Percocet, I was basically almost better. So I suffered for 3 or 4 days walking around on it. So finally we got this whole prescription. But I mean, the pharmacist, when they got the 2 different prescriptions, they had to go through all these different hoops to, you know, take back the old prescription. I had to bring it back in. They could see I didn't take any pills. So, I mean, there's a lot of checks and balances there, which I think are good, having these systems communicate with each other. But now you have the flip side problem where I think doctors are now gun shy to prescribe when they should prescribe. So I really was interested in the German system, where it's like, hey, you need a shot, you go to this place, you get your shot, and you start, if you're showing up there a little too often, that's a problem.
It was actually being discussed here in the US, and recently Trump just was totally against those safe injections place.
Interesting.
So it's totally down here in the US now. But it's interesting. Another thing that so the company that I work for, we have a software that, so we work closely with the softwares where the doctors do their prescriptions, you know, the software that they put the drug and send to your pharmacy, and then you go there, pick up the drug. So every time they try to prescribe opioid, we pop up a couple different step therapies for that specific treatment. But it depends on, so for the doctor to actually prescribe an opioid, when they have this software, they have to go through a lot of points, you know, yes, I agree, yes, I know this, I know that. So it's not something so automatic. And yes, there are a lot of other opportunities for data science to work on this.
So how you can't really measure pain, I think UWM is making a research trying to create a scale for measurement of pain, but basically evaluating data from patients in diverse types with diverse problems to see if they can get to a point, because right now it's basically impossible to measure pain.
Yeah, I also have a personal experience with that. I know we're totally over 20 minutes. But
yeah, let's make this the last question, and we'll.
Surgery, and I was prescribed in Brazil, actually. Which, fun fact, since the opioid crisis started here in the US and they stopped selling so many opioid drugs here, the industry in Brazil increased 487% in a year. Nobody talks about that there. Nobody talks about that. Nobody knows anything about it. So the point about with how you measure pain, I was prescribed with some opioids, and I had no idea by that time. I was actually just taking them to sleep because I wasn't feeling that much pain. And how much the users know about, how much the doctors actually can measure the pain to say, hey, Priscilla, you needed this opioid. I actually did not need at all. I was just using to sleep. So, misuse. Thank you, guys.
All right, so we have Galib and then Karan.
Why is it coming like this? It should be like this.
Well, let's see if maybe if I hit play, it looks better.
No, it's okay. Just the time will not zoom, not the images.
Okay.
Okay.
Hey, Dr. Littman.
Here, I'm going to talk about home automation systems and networking related to it. So, starting with a little bit history of home automation. So, In 1975, there was a first general purpose home automation network technology called as X10 was developed. It is a communication protocol for electronic devices. It primarily uses electric power transmission wire for signaling and control, where the signals involve brief radio frequencies burst into digital data, and and remains the most widely available thing. By 1978, X10 products include a 16-channel command console, a lamp module, and an appliance module. Next.
It's me.
Yeah, you're not sure.
Oh, I'm not sharing it? Are you sure? It's actually probable. I was so caught up on making sure my mic was, well, no, I'm sharing my screen already from
And now
by default.
I
I'm sharing
cannot
my
see.
screen. Aren't I? Oh, no. Okay, you're right. Sorry.
Got it.
Apologies. Yep.
Okay. So, some revelations, in the early 2000s or 1998, smart homes or home automation began to increase in popularity in the early 2000s. As such, different technology began to emerge. Smart homes suddenly became a more affordable option and therefore a viable technology for consumers. Domestic technologies, home networking, and other gadgets began to appear on store shelves. And today's smart home are more about security and living greener. Our smart homes are sustainable and they help to ensure that our homes are not expending unnecessary energy. They help. They also help us to They also help alert us for the intruders or something like that. Next slide. Okay. So talking about the home automation protocols, I'll talk about four of them. There are many: KNX, C-bus system, ZigBee that they are discussed about, and the Z-Wave. Okay, so next slide. KNX. As of March 2014, there were 339 members and from 37 different countries who were the manufacturer of this protocol. KNX is designed to be independent of any particular hardware platform. A KNX device network can be controlled by anything from an 8-bit microcontroller to a personal computer. It depends according to the need of particular implementation. The most common form of installation is over twisted pair medium. Twisted pair medium is it's sort of a cable type of wiring in which two conductors of single circuit are twisted together for the purpose of improving electromagnetic compatibility. Next slide. Okay. The other one is C-bus. C-bus system can be used to control lighting and other electrical systems and products automatically or via remote control systems, and can also be interfaced to a home security system. The C-bus system is available in a wired version and a wireless version with a gateway available to allow messages to be sent between wired and wireless networks. The third one is ZigBee. ZigBee is the research project of IEEE, this volume 802.15.4. It is used for the high-level communication protocols used to create personal area network with a small, low-power digital radios, such as for home automation, medical devices, data collection, and other low-power, low-bandwidth needs designed for small-scale projects which need wireless connection. Hence, ZigBee is a low power, low data rate, and close proximity wireless ad hoc network. Next. So Z-Wave is the latest protocol that is nowadays being used in the home automation or the automation technologies. It is a wireless communication protocol used primarily for home automation. It is a meshed network using low energy radio waves to communicate from appliances to appliances, allowing for like wireless control of residential appliances and other devices such as lighting control, security systems, thermostats, windows, locks, and other things. Z-Wave, like other protocols and systems aimed at the home and office automation market, Z-Wave automation system can be controlled via the internet from the wireless key fob, a wall-mounted device, or something like that. Next slide. Home automation based on IoT. So Internet of Things conceptualize the idea of remotely connecting and monitoring real-world objects through the internet. When it comes to our house, this concept can be aptly incorporated to make it smarter, safer, and automated. Next slide. Let's talk about Echo and Alexa. So Amazon Echo and Alexa. Alexa is an intelligent personal assistant developed by Amazon, first used in the Amazon Echo and the Amazon Echo Dot devices developed by Amazon Labs. It is capable of voice interaction, music playback, making to-do lists, setting alarms, etc. Or you can it can provide you weather and traffic real-time information. Alexa can also control several smart devices using itself as a home automation system. You can change Alexa's name and many other things. Next. So it's okay. So I've written the text over there. It's not only Internet of Things, it's Internet of Everything. Talking about Internet of Everything nowadays is most common thing. If we it is the term Internet of Things is like Internet of Everything, sorry, is overlapping it. It is considered as a superset of IoT, Internet of Things. In Internet of Things, the concept is that communication is dropped to machine, like machines itself are communicating with each other to make to learn the environment and to make their decisions on its own. This is what Internet of Everything is nowadays. Okay. Yeah, future of home automation. The future would be advanced sensor and artificial intelligence, which is implemented. Till the date, home automation has been looked up upon as something to not only on off your devices from mobile phone, but the scenario is changing. Regular automation combined with smart wireless network of sensors started to understand the human environment. Sensors like motion sensors, temperature sensors, light intensity sensors, uh, smoke detectors are being accommodated with home automation, and the data from these sensors would further be used to analyze, to understand the patterns, and in turn with deep learning used for intelligence of the device itself. According to a research, the global market for the home automation is projected to rise from 4 billion to 21 billion by the end of 2020. In the near future, smart homes will become as common as the internet today. Otherwise, it will be outdated, just like the home today without an internet. That's it. Thank you.
All right. Questions?
Did your research look at anything with the network security associated with this home automation stuff? I know historically IoT devices are known for being security vulnerable.
So I have a TED talk related to it that describes this thing, that a lady, she was on a mission to automate her home, but she took a practical or something, she experimented the thing. she make her single room fully automated with all the things, and there was like and she uses a router. Someone I forgot mentioned that you mentioned, sorry, your router thing, Unify. Yeah. Okay, so she uses something like that. I don't know, I remember the company name, but that router like manages and tells us that whatever devices you are using in your home, what data is being collected from them. Like she mentioned the Amazon Echo device, all the stats and all the like all the daily routine of her is being monitored on that. And she kept on reading all the data sets that is being trained by that is trained itself by Amazon Echo. So these are some of the security related things that are in the automation industry.
Even Amazon Alexa stores what are yours Amazon Alexa.
Yeah.
Anything else? All right, we have Karan, and then we have Josh.
Yes.
Are you doing it on yours or are you doing it on yours? Okay. So let me stop my sharing. So now you can start sharing.
Hello. Yeah, it's recording, right?
Okay. Yep.
Yeah. My topic is okay. Yeah. My topic is TCP/IP protocol. Yeah. The TCP protocol stands for the Transmission Control Protocol, which said for the networking protocol that allow two computer to transfer data from one computer to another. The network failed. In network failed, the basic knowledge of computer networking is start from this level. The TCP/IP protocol is one of the famous node of communication which we use in to get data transfer by an internet access. We can send and receive the messages by internet signals by two node. TCP/IP protocol layers, they use mainly for OSI layers in TCP protocol. First is application layer that use the HTTP files like hypertext transfer protocol, FTP like file transfer protocol, and SMTP simple mail transfer protocol. The transport layer, the transport layer provides the end-to-end communication. When the message is passed from one computer to another, it provides whole communication by this layer. The internet layer is responsible for the package which is sent to the receiver that should be sent by the internet. So this IP protocol used for this purpose, like internet protocol. The physical layer is just for the interconnection between the nodes. Like for connection of two computer, it's used for the physical layer. Now we can talk about the OSI models. The OSI is the International Standard Organization developed the OSI model for the. They are having a seven layer of network communication. The first 1 to 4 are lower level of communication, and the 5 to 7 are the upper level of application level. Each layer has a specific job, and their main thing is like to main thing is for basic principle is pass it on. There is a simple transmit data by physical link, and then they receive the data to user. Here are the 7 layers. The physical layer, as we say, that it's for the median to means when we send the message to another computer, it's just a median. The data layer, the data defines for the format of data to the network. Then network layer is the physical path of the data that we send to the another computer. The transport layer will be communicate with one computer to another via TCP or UDP. UDP and UDP stands for user data protocol. The session layer will responsible for controlling the ports of the connection and session. The presentation layer will usable format of data encryption occurs. Like when we send some data which is not encrypted, it will be encrypted by this layer. The application layer is the final layer that interact with the all application can access the network services. Now I will discuss about the type of attacks in networks. Like there are mainly 3 type of attacks. One is active attack, second one is passive, and another one is advanced attack. Active attacks means they are having a spoofing attack, wormhole attack, and modification and fabrication. Spoofing, when the message is sent from one node to another, it can so the sender can change the topology of the message. When the modification of the data is done by the modification attack, like when we send some data to another person, the routing of the sender will be changed, and the means the communication will be delay, and the sender will not get the message. Wormhole, this attack is also tunneling attack. It's attack like the attacker receive a packet from one point, and the another point it will be a malicious. So the show it when we send one packet to the receiver, it will be having a it will be having malicious on that part, but the malicious thing will be happen to the another route that will be sender receive, receiver receive. So receiver will be thinking that this is a shorted path, so this is the correct path of communication. Fabrication is like when we send something to another computer, they can fabricate message, like they can be having something fabrication of message. Passive attack. There are 3 passive attacks, like traffic analysis, eavesdropping, and monitoring. Traffic analysis is an attack tries to sense the communication path. When sender and receiver are connected, this attack can be done, and the amount of data has been transmitted, that all can be that all can be modified, and that can be saved in the attacker. The eavesdropping, this is the passive attack which occurs in a mobile ad hoc network. The main aim of this attack is to reach out the secret information of the communication, and this while transferring some information, they can also have uh, they can also track the public key and private key also. Monitoring attack, this attack is just for the monitoring of what we are transferring the data. This attack cannot train the data, but just for watching the data what we are transferring. The advanced attack, the advanced attack nowadays is more popular, the black hole attack. One of the advanced attack which attacker use to routing protocol is the black hole. And a hacker use a floating base protocol to list the request of a route for the inhibitor. The hacker create the reply message for the shorter path, and to the receiver. As the message received by the hacker to the receivers thought that it is this message is received by the sender, but this is not. This message was not sent by the receiver. The hacker sent the message. So this way the communication will be break and malicious activity can happen. Reply attack is the attack, a malicious node may repeat the data delay by the data. This attack may be the data loss or have the data delay to the receiver. Location disorder attack, malicious node collect the information about the node, and it can be collect all information with the location where the monitoring of the data is being done. So this is a very dangerous malicious node, perfect by the attack. The first computer to computer data transfer was done by the ARPANET, Advanced Research Project Agency Network. The pursuer to the internet, October 29, 1969. The package switching on the ARPANET was based by the design by British scientists Donald Davis and Lawrence Robert of Lincoln Laboratory. The message was just login to, the word was login, that was passed one computer to another computer, but first it was being break and just L and O was passed. Then after an hour of breakage, the whole message was passed. That's it.
Now, for that last example, that was using TCP/IP.
No, it
So
was
it was a different
paper.
Yeah,
It
gotcha.
was just a pair-to-pair link, like
Yeah.
basic.
Well, because what would have been interesting there, let's pretend like it was using TCP/IP. One of the things TCP/IP does is it guarantees the data eventually arrives. That'd be interesting if one computer sent it and a couple of the packets arrived, and then like an hour later, once the network recovered, it finally spit out the rest of the word. Like, look, I said you get it. I didn't say when. Any questions?
Thank you.
All right.
All right. So
Okay.
you're up, Josh.
Yes. Hope you can see my.
Let me update my sound real quick. All right. Go ahead and try talking. Let me make sure I got you.
Yes. Can you see my screen?
Yes, we can, and we can hear you.
Okay. Yes. Thank you. This is interesting. So anyway, good evening to everybody. And today's my research topic is OSI model. As you know that just before me, Karan has spoke about test OSI model. And I will be, basically, I will be talking with you about OSI model, all the layer from 1 to 7 layers. And that's what. So OSI model is stand for the open system interaction. So, and this OSI model is actually made in a conceptual model which can be which is developed by the International Standard Organization in the year up to 1984. An OSI model divides networks communication into the 7 layer, which we are going to see in next slide one by one, and what the 7 layers is talking about. And main thing is that in OSI model is very good to understand at the basic and a big picture of network. Through the OSI model, we can understand even the hardware and software, how the hardware and software work together. Even though OSI model, through the OSI model, we can understand the new technology which already has been developed. So let us see, these are the 7 layers. as we see, these are the 7. In this model, 1 to 4 layers is consists as a layer. This lower layer is very good for the moving the data around, and the layer from 5 to 7, which is called upper level layer. An upper level layer is all contains application level. That's what, and especially in these 7 layers, each layers have a specific job to pass data around one node to another node. That's the main things in these 7 layers. Let us see, talk about each layer from starting from the bottom. First is coming a physical layer. Physical layer is responsible for the actual physical connection between the devices. As you see the picture, there is computers and Ethernet hub and internet cables. These cables are connected with each another physically. So the physical layer is contains information in the form of bits. It is also responsible for transforming individual bits from one node to another node. And also, physical layer receives data. This data signal received and convert into zeros and ones, and then send them the data to link layer. Let us talk about this. Is the main function of second layer. Especially second layer is a very specific specialty it has to make sure it's making sure the data transfer error is free. It should not be the error. It should be error free. Data link layer's job is to making sure that data error is free from one node to another node. When the package arrives in the network, it is responsibility of data link layer to transmit it to the another host. For example, if you see PPP, which is a point-to-point protocol, and ATM. Network layers. This third layer is a network layer. This third layer is good for the transmitting the data from one host to another host in different network. As we see in the picture, there are the different networks, are there server, network, and clients. So this network layer is good to transmit the data from one network to another network. And that example would be just like a DDP, this diagram deliver protocol, IP, and etc. The fourth layer is a transport layer. This layer provides service to application and take service from the network. It provides a service to the application and take a service from the network layers. And the data in the transport layer is called segment. It is also responsible for the end-to-end delivery of the complete message. For example, could be SPX, which is a Square Packet Exchange, and TCP Transmission Control Protocol. the session layer is the fifth layer. This session layer is responsible, especially responsible for the establishing, maintaining, and terminating session. And also, the session layer has a specialty to also session ID is used to identify a session or interaction. For example, remote procedure cell, which is RPC, SQL, and ASP. This sixth layer is called presentation layer, which is also called translation layer. The data from the application layer is executed. As you did see in the picture, data from the application, data from a application layer executes and manipulate and also transmit over the network. The function of presentation layer are translation, encryption, and decryption and compression. Example would be if you can see in the web browser and HTTP. The seventh layer and the top layer is the application layer. These application produces the data which must be transformed over the network. This layer is also good for Windows, for the application to access the network, and for the displaying and the receiving information to the user. The function of application layers are mostly in network virtual terminal and FTAM, which is file transfer, access, and management. Even though in the mail service, that's a good access in the data layers. And I would like to say this in the 7 layer to memorize is a good way. This acronym of to memorize this 7 layer from the 7 to 1 would be good. To please do not throw sausage pizza away. Interjecting half layer. In this model, people could not really decide where our protocol belongs. It may be its layer from 2 or 3. So half layer was made between the 2 layers. The same layer was between 4 and 5. Then it top layer of the 7 layers. And if you can see in the picture, this is application layer, transport layer in the right side of the picture, application layer and transport layer and internet layer and network layer. Thank you so much. If you have any question, you can ask.
Yeah, that was a good job. I think that was actually a pretty good time, well-timed presentation given all the stuff that we've already talked about tonight, because this gave more of the high level of what all of those different steps actually look like. So I thought that was actually pretty informative, and your sausage pizza thing will definitely get you extra credit. Anybody have any questions? Now that last slide you just showed, that was showing the difference between the 7-layer OSI model and TCP/IP, right?
This last slide, this one, yeah.
Yep. Yeah. So yeah. TCP/IP compresses those top 3 layers into a single application layer. That's the difference between those 2 things, and that's where I got confused on your slides. You transitioned from 2 different papers, right? He started off like this whole thing's going to be on TCP/IP, and then he's on OSI. He's like, he's showing 7, it's only 5. Okay, yeah. So, questions for Josh? Okay. And last but not least, we have Debbie. And then you're doing on yours?
Yeah.
Okay. My
Now
mic
I
off,
can hear. Yeah.
or my mic on. Everybody can hear now. Just
Yeah, I
talk,
can.
you'll be good.
This is disturbing.
All right, stop messaging on Slack. He's getting. Right. Good.
So previously we used to use coaxial cables for communication, but later we started using optical networks because we need to overcome the issues which we had in coaxial cables, like cable cost and signal loss and long distance communication, which is not possible in coaxial cables. And also the bandwidth speed is comparatively lesser than optical fibers. So in optical fibers, the signal loss is comparatively lesser than around 0.4 dB per kilometer. And I'm not sure how much signal loss there was there in coaxial cables. I just didn't refer to that as it is not necessary in this topic. And we have 6 generations of optical fiber communication. In the first 1 to 4 generations, we use a technique called CWDM, which is a category of WDM technique. WDM is nothing but wavelength division multiplexing. So what wavelength division multiplexing actually is? So it's kind of everybody is aware of a prism experiment, which we did in electronics and communications for them. So it's an inverse version of it, where the multiple wavelengths are transferred in a single fiber, and then again it is distributed at the receiver end. These are different wavelengths which we transfer on a single fiber optic cable, and then they are distributed again. So this is a multiplexer which is used to combine these wavelengths and transfer it through the cable. And here we use demultiplexer, which divides the signals and transfer to the receiver end. So there are 2 categories of wavelength division multiplexing. It is CWDM and DWDM. And CWDM is nothing but it's coarse wavelength division multiplexing, and DWDM is dense wavelength division multiplexing. CWDM is nothing but, let me explain here. 1 minute, I'll just get my mouse. In CWDM, what actually happened is, let me explain this first. In dense wavelength division multiplexing, this is architecture of dense wavelength division multiplexing, where we use OADM, which is an add-drop multiplexer, which can add an external wavelength in the fiber after transferring the various signals to the optical fiber. And here we use amplifier, which is used for long distance communication, because as the distance get increased, the signal gets weakened. So to transfer this sensitive information, which is having low signal power, we use amplifier so that the receiver end can get actually the actual signal power which was transmitted from here. In CWDM, we don't have this add-drop multiplexer and amplifier. We just use the normal, the first generation WDM technique, where we don't have any amplifier to which we use for long distance communications. And also the channel spacing is comparatively higher than WDM. So this is called channel spacing. This is actually wavelength. If you consider these are channels, so this is a channel spacing. In WDM, the channel spacing is around let's take this is an optical fiber, and if we in CWDM we are able to send only 8 to 12 channels per fiber, but in DWDM we are able to send 8 to 40 channels per fiber. So that's the basic difference between CWDM and DWDM. And so DWDM is the current generation, which is 6th generation of the optical fiber networking. So in the 6th generation, we almost reached the Shannon limit. What Shannon limit is so this is the equation for Shannon limit, where the signal strength gets weakened with the noise ratio. How the signal strength gets weakened, because nowadays we are using Gbps speeds in the way, through optical fibers, because of which the the traffic gets increased because number of users keep number of signals gets increased in the fiber, and we don't have any option for adding or dropping the signals because it's a continuous spectrum. So the signal, the traffic gets increased, traffic gets increased, and because of the traffic, we have a increase in noise also. So as the noise increases, the signal power gets decreases, which ultimately gets to 0. And because of this, the logarithm, the channel bandwidth also gets 0. Then we will reach a point where we cannot transfer any data. I mean, we can transfer, but there is no point in transferring because the receiver end cannot receive the data because of the traffic. Next, so to overcome this Shannon limit, people propose this elastic optical network, which uses a technique called OFDM. It's an orthogonal frequency division multiplexing. I'm going to explain that so that you can understand properly. So what basically happens in orthogonal in elastic optical networking is, let's say this is a channel and we are sending a signal from A to C. Like from A to C, we have request of 200 Mbps. But in what DWDM is having, DWDM is having is, it is having a fixed wavelength slots. So in fixed wavelength slot like this, this is a fixed wavelength slot of 100 Gbps line, and this is also fixed slot of 100 Gbps. This is also fixed length of 100 Gbps, but we are sending 40 Gbps data from F to C because it is we need to send from A to C. To transfer F to C, we need to go through A to C, which is using a 100 Gbps line. So we need to utilize this 100 Gbps line to send 40 Gbps data. Same goes with B to C also. It is using the same 100 Gbps line, and it is also sending the same 40 Gbps data, which results in loss of bandwidth. I mean, they are not utilizing complete bandwidth, where we cannot send data from D to E because it's already filled with F, A, B, and C. So to overcome this, we introduce a technique called flexibility grid allocation. What happens is here, instead of having a fixed wavelength slots, we'll just divide it as per the request. Let's say from A to C, I'm sending a 200 Gbps request data. So instead of dividing it into 200, as it is a 100 Gbps line, I'm going to send 200 Gbps line on 200 Gbps on single 100 Gbps line with an amplifier. And from F to C, instead of sending 40 on 100 Gbps line, I'm going to send 60 because the distance is high and we need some repeaters to cover the signal loss. So I'm going to use 60 Gbps wavelength slot. And from B to C, I'm sending a 40 Mbps request. As the distance is low, we don't need any amplifiers, so I'm going to stick with 40 Mbps wavelength slot. So thereby, we left with 200 Mbps slot in this 100 Gbps line. That's how the flexible grid allocation works. And this helps the elastic optical networking utilize the complete bandwidth, which helps to transfer D and E data also to C whenever it required. And it also uses a technique to reduce the channel spacing. The technique is called OFDM, which is orthogonal frequency division multiplexing, where what happens is instead of using these gaps, the signals are overlapped. What happened in traditional DWDM multiplexer is it uses guard bands here so that the signals won't interfere here, and noise gets induced because of that if the signals get interfere. You may ask, like, if the signals are interfering in this case, how does the noise is reduced in these cases? So that's how that's where we use orthogonal frequency division multiplexing. This is how signals are overlapped. Let's say this red signal is A and green signal is B, blue signal is C and D respectively. When red signal is at peak point and this blue signal is at 0 point, green signal is also at 0 point, and this purple signal is also at 0 point. Means those are all inactive. Only this red signal is in active state. So when this green signal is in peak point, the red signal is red and the other signals are at null point, 0 point, which means there are inactive states. So that's how the signals are differentiated and transferred. This technique is basically called orthogonal. So that's how we got orthogonal frequency division multiplexing. So this is a basic architecture of EON, and electrical optical networks are also called as flexible grid optical networks, because we are using flexible allocation instead of fixed allocation, which is an default optical networks which we used previously. But there are few limitations for elastic optical networks, which are we use most effective hardware development for that. One of that effective hardware development is, let me show you that, this BVT and BVWXC. So this is a tool which is used for OFDM. So this tool converts the signals into OFDM signals as yes, like this tool converts the signals into this format, and this is the demultiplexer which divides the signals and sends it to the receiver end. So Microsoft is trying to implement these techniques in a different way. So Microsoft using this line system technology and photonic layer disintegration and bandwidth variable transceivers. So these three uses these two tools to utilize the elastic optical networking. But what this line system technology does is it's only suitable for point-to-point communication. It is not suitable for long distance communication because the complexity increases as the orthogonal frequency division multiplexing when the demultiplexer tries to separate the signals, because long distance communications have slight noise, and the noise signals will also interfere with the orthogonal signals here. And in photonic layer disintegration, what it's basically it's related to the network field, which network side end, like so what this photonic layer disintegration does is they operate remotely, and they just reduce the wavelength capacity like how here we are using the add drop multiplexer. The same process is done by the photogenic layer disintegration, but it's in an advanced way, which still Microsoft is working on. And bandwidth variable transceiver is nothing but the same thing. It's a demultiplexer of the advanced generation. It's still under research, and we don't have any proper information on this. And I struggle to get proper information on this as well. I got only one research paper on this, which is in IEEE, which is a paid version, so I can't get it. So that's about elastic optical networking.
Okay, you're just under 18 minutes. Cool topic. Actually, let me turn this on here. Oh, I already have mine on. I actually think the topic is a really cool topic. Way too technical for a 10-minute talk. But if we flip onto the positive side, it was clear you understood it. So I think that you probably did a lot of research, a lot of looking into this. So I'm impressed with your knowledge on the topic, but way too much detail for 10 minutes. So having said that, any questions on the talk?
I mean, I can cover the details about the WDM bandwidth rates and DWDM bandwidth rates, but it's not necessary because my topic is just elastic optical network.
Right. Any questions? All right, so let me say a couple things here in our last couple minutes. So let's see, let me just make sure I mark down the time real quick. One thing to keep in mind for the next presentations is everything can't be most important, right? So you got 10 minutes to present a topic. You have to decide what can fit inside that 10 minutes and what are the things that you definitely want to get out to the audience versus getting up there and saying, here's 4 million things, I'm going to somehow compress it into 10 minutes. Oh, but by the way, no, I'm not. So, you know, our several presentations tonight went, were very good length. Some went very long. So I encourage you to practice your presentations at home. I mean, you don't have to get up here and memorize it. I'm not looking at this to be this crazy professional presentation type thing like you're doing a keynote somewhere, but you know, you should have a pretty good idea of how long your presentations are going to be before you come in. So I would expect presentations to be in like the 9.5 to no more than 11-minute range if you've practiced it, something like that. All right, so keep in mind we're on a 10-minute clock. I think what we might do next time, I've seen it happen in hackathons and things like that, where at the 10-minute mark, I'll like put a finger up and you got like 30 seconds to wind down, something like that. Well, we'll figure out what that looks like. But I want to make sure everybody gets treated the same. So that's why I let several of the talks go longer today, since some of the early ones also went longer. So that way we get to see where everybody spills out. So we might do that next time where talks won't go over maybe 11 minutes, something like that. And your last word is the word "and" or something like that. It's just going to be the way it is. It's the end of the talk. All right, so I encourage you to practice those for before the next presentation. So next week we're back on to lab day, right? All right, so as usual, I'll be here. Encourage everybody to show up and work on your next embedded systems labs. If you would rather do that on your own, feel free. But I'll have the Zoom meeting up for everybody to work on. Questions?
What's the next topic?
Concerns, bribes? Oh, go ahead. Yes.
Computer architecture, yeah.
Oh, ideas. Okay. Oh, before I answer that real quick, we will have one presentation next week. Ani had an excused absence this week, so she'll be here next week to give her presentation. So computer architecture. I like mobile architecture type stuff, so maybe hardware related to cell phones or other mobile devices, things that are running off of batteries.
Let's see. If I was researching computer architecture,
I have found one
I
topic.
mean,
Yeah.
quantum architecture could be kind of cool. I kind of hope somebody does that. Maybe a focus on quantum architecture for the layperson. So instead of, here's the details of, qubits and on, off, or flip, actually breaking it down into how do quantum computers work relative to traditional computers for a normal person. So we can kind of imagine what that looks like. So quantum computing, I think, could be a cool thing, but specifically about the architecture of it as opposed to, I guess, the software side. But I guess they're so related that I don't know that that matters. So I guess I would, if you were looking for my two top ideas, something about mobile processors or mobile hardware and the decisions that they have to make related to it being mobile, and then quantum. I think both of those sound pretty cool. Oh, I got one more that would actually be kind of cool. This is good, be a little sci-fi, a little out there, but looking at nanotechnology and like nanites for creating ubiquitous computing systems, effectively invisible computers. How might that work? I think that is effectively computer architecture that's invisible. I gave a talk a while ago. I think I've mentioned it before in class that I actually think that before we find a cure for cancer, we'll use nanotechnology to solve the cancer problem by effectively having an army of nanites inside your body that will just, using machine learning, things like that, target cancerous cells and destroy them. You still have cancer. The cancerous cells are at bay because you have an army of nanites keeping them that way. I think we might look at the future of medicine and kind of see a lot of things where we decide, well, we can't cure this, so we'll just make it so it's not really a problem. I think that could be kind of an interesting thing. That could have actually been an interesting, we bordered on it with some of the personal area networks for tonight, but I think the idea of nanite-based networks where you have these microscopic sized computers and now we have the technology that allows us to have radios in something even that small. How do they communicate with each other and create kind of cloud-based micro networks that could fit on a, microscope slide, something like that. Yeah, so if you want to go freaky deaky with it, I guess, go into nanotechnology.
Does it have to be computer architecture, or is anything kind of hardware?
Well, okay, so that's a loaded question. So I would say that you should be able to, at the very least, weakly connect it to computer architecture. But if you stumble upon a really interesting idea that really excites you, just send me the idea and say, hey, can I do something on this? And unless it's just so far off the reservation, it's probably fine. But if you don't think that you can connect it to architecture, then at least check with me for the topic to, at least that way in class, if you give a topic and I can defend you and say you had permission or something. Cool?
But you said architecture, that is fine.
So who, what?
So you just said that anything related to architecture is fine.
Yeah, isn't that the topic?
It's computer architecture, which is what my question was.
Oh, yeah. Well, yeah. So anything related to architecture in general, I guess, wouldn't be fine. Like, I mean, you should have something like a house building.
But like, I don't know, like robots and stuff.
That's computer architecture. Yeah. So I mean, yeah, it should relate to computers, technology, and at some things. So stuff with robotics, things like that is fine. But yeah, not house building, right? Unless it's a really cool topic, like.
Yeah.
I actually am very interested in that. Or how about nanite building houses? Wouldn't that be cool? Somebody just shows up with like a syringe and just and also. I tell you what, we laugh about it right now. In the next 100 years, stuff like that will happen. You watch Stargate, the one of the alien races, they use crystals to build tunnels underground. They have the different shapes like Tetris, but that's the way things are going to work. No more of these hammer and nails and stuff like that. All right, I'll see everybody next week. Oh, hold on, Josh. I'll turn my audio on real quick so you can say goodnight. All right, you're on. All right, Josh says goodbye to everybody.
Goodbye.
Bye. See you next week. Bye.
See you next week. Thank you.
See the two of you next week. Bye-bye.
Bye-bye.